Hello friends, welcome back to our channel. So today we'll see one more concept in algorithms, that is dynamic programming. So this is one algorithmic approach in order to solve the programs or problems. So in our previous sessions we have seen the greedy method and divide and conquer, and now we're moving on with the next concept, that is a dynamic programming. So this is similar to our divide and conquer method. So usually the divide and conquer method is represented as DAC, divide and conquer, and this is represented as DP, so which is abbreviated as a dynamic programming. And the main goal is this dynamic programming approach is used to solve optimization problems. I think we have seen this in the greedy method. So greedy method is also used to solve the optimization problems, and here also it is used to solve the optimization problems. So we know that optimization problems are the problems which are having a multiple solutions, and we are selecting the optimal solution based upon the constraints, right? So that is an optimization problem. And so working is similar, not equal, right? It is a similar to divide and conquer. That means here also the complete problem will be divided into sub-problems, similar to our divide and conquer. But only one thing difference is, so the division should be with overlapping sub-problems. Okay, with the overlapping sub-problems. So overlapping sub-problems. But in case of divide and conquer, so the sub-problems will be divided without any overlapping solutions, right? So let me explain what is exactly the overlapping sub-problems and the not overlapping sub-problems. For example, so in both the cases, I'll write the steps and then I'll differentiate these two things. Okay, so the first step 1, the first step, the complex problem will be divided into sub-problems. The complex problem is divided into sub-problems. So either it can be a complex problems or a large problems. Okay, and step 2. So this is common with the divide and conquer. Next we have to find out the solution for these sub-problems. Here also find solutions, that's also optimal solutions. So here that is important. Find optimal solutions for all sub-problems. Okay, here this is also common. And step 3, this is the most important and a unique among the remaining algorithmic approaches. So store the solution of sub-problem in the memory. Okay, so stores or save solution of sub-problem, so that if it requires to get a solution for the same sub-problem some other time, so in order to avoid that one, so we can get the solution from the memory. So we have to find out the optimal solutions for all the sub-problems, and we have to save the complete solution in the memory. And before solving the subproblem, first we need to check in the memory whether there is a solution for the subproblem. If it is there, then automatically we can retrieve the value. Otherwise, we have to solve the solve the problem and get the optimal solution, and again save the same thing in the memory. So this is a unique thing. Okay. For example, consider the Fibonacci series. Okay. See. So I'll write the step 4 also, the last step. So what is the last step? So finding the complete solution for overall problem. So based upon the optimal solution. So from all optimal solutions, from all optimal solutions of subproblems, find out overall solution. Find out overall solution. Find out overall solution. So these are the main steps that will be followed in this particular algorithmic approach. The first one, complex problem, will be divided into subproblems, and second, find the optimal solutions for all the subproblems, and the third, stores or saves each solution of the subproblem and for the future reference. And step 4, from all optimal solutions of the subproblem, find out the overall solution. See, now I will tell you the example of overlapping subproblems and non-overlapping subproblems. Example, let us consider the Fibonacci sequence. Fibonacci sequence. Alright. So, we know that Fibonacci sequence means the element is nothing but the addition of previous two elements. The element is addition of previous two elements. For example, so if the first element is 0 and the next element is 1, the next element will be 1 plus 0, it will be 1. Next element will be 1 plus 1, 2. Next element will be 2 plus 1, 3. Next element will be 3 plus 2, 5. Next element will be 8, next 13, 21, etc. So how we got a 21? So 21 we got with the addition of 13 and 8. How we got a 13? 13 addition of 8 and 5. How we got a 8? Addition of 5 and 3. So n is equal to n minus 1 plus n minus 2. So if you want to get n minus 1, n, so we need to add n minus 1 and n minus 2. So we can solve this one by using the recursion. Okay, simply we can use the recursion. Fibonacci of n minus 1 and n minus 2. So if you solve the same thing using the recursion, what happens? Let us see. See, if you want to solve, for example, Fibonacci of n, how we can solve? So this can be done with the help of Fibonacci of n minus 1 and Fibonacci of n minus 2. Okay, then how you got n minus 1? Again, Fibonacci of n minus 2, Fibonacci of n minus 3. Alright, and what about this one? Fibonacci of n minus 3, Fibonacci of n minus 4, and the process will be repeated similarly. So here you can observe, so Fibonacci of n minus 2, here we are solving, and the same thing we are solving here also. Fibonacci of n minus 3, here we are solving, and also we are solving here. Similarly, Fibonacci of n minus 4 is solved here, and somewhere else definitely we will solve the same thing. So that means that repeatedly we are solving the same thing multiple times, even though it is a recursion, right? So instead of that one, if you solve the solution, if you get the solution for this problem, that will be stored in a table. Okay, so simply here I'll write Fibonacci of n minus 2. So whenever it is required here, I need not execute the same thing, I need not implement the same thing. So I'll get the value from the memory because it was already solved and it was already stored. The solution is already stored in the memory. Right? So consider these are all the subproblems. These are all the subproblems. So once you solve the subproblem, the solution will be stored in the memory. Right? And this process is called top-down approach. Top-down approach. And this process is called as memorization. 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 So here the same problem can be solved in two different approaches. One is the top down and the bottom up. Okay, so bottom up approach. One more thing, we can write a bottom up approach. So that means the solution will be getting from the base case itself, right? So this process we call it as a tabulation. Tabulation. Okay, tabulation, right? So hope you understood. So these type of subproblems we call it as a overlapping subproblems. So here we are having a Fibonacci of n minus 2 and here also we are having Fibonacci of n minus 2. The same problem repeated twice here. So this process, these two subproblems, we can call it as a overlapping subproblems. Overlapping subproblems. So this the one characteristic of dynamic programming is overlapping structure. Overlapping structure. Okay. So I'll write down here. Characteristics. So one is overlapping structure. So actually in the dynamic programming we are also dividing the problem into subproblems but without overlapping subproblems. And the second characteristic is an optimal solution, optimal subproblems. Optimal subproblems. That means here also, as we discussed just now, so consider each and every subproblem and we have to find out the optimal solution for each and every subproblem. Right? So that we call it as an optimal subproblem. And these two we can say as a characteristics of dynamic programming. Dynamic programming. See, I'll write here. Consider these approaches. Approaches. So we can say this as a top-down approach and two approaches. Another one is a bottom-up approach. So in this top-down approach, we call the process as memorization, and here it is called as tabulation. And here we'll use a recursive function. Recursive, right? So every subproblem will be solved by using a recursive, and here this recursion will be avoided and here it will be iterative, right? So these are the different approaches to use this dynamic programming, to solve any problem using this dynamic programming approach. And now let us see the applications. So what are the applications or what kind of problems can be solved by using this dynamic programming? So as we just discussed it just now, that is Fibonacci sequence, multi-stage graph, matrix multiplication, matrix multiplications, 0-1 knapsack, towers of Hanai, of applications are there. So lot of applications are there. So these type of problems can be solved by using this dynamic programming in order to get the optimal solution, right? So hope you understood the top-down approach and bottom-up approach, and overlapping subproblems and not overlapping subproblems. So that's the main difference between the dynamic programming and the divide and conquer. Divide and conquer, the division will be done without any overlapping subproblems, and but here dynamic programming will be divided with a overlapping subproblems, right? The characteristics, overlapping structure, and the optimal subproblems. So hope you understood. So let's stop here, and in our further sessions we'll move on with the applications. We'll take some problems and we'll see how we can solve the problem using this particular algorithmic approach, dynamic programming, right? So let's stop here. Hope you understood this one, and if you are having any doubts regarding this one, feel free to post your doubts in the comment section. Definitely I will try to clarify all your doubts. If you really enjoyed my session, like my session, share my session with your friends, and don't forget to subscribe to our channel. Thanks for watching. Thank you very much. Hello friends, welcome back to our channel. So today we'll see one more concept in algorithms concept, that is 0-1 knapsack problem. 0-1 knapsack problem. So before going to this problem, first let us understand what is meant by a knapsack and what is meant by 0-1 knapsack. So we know that a sack means it's nothing but a bag. So here the problem is we are supposed to fill some objects into that bag with a highest profit. So let us consider 4 objects, right? Some x1, x2, x3 and x4. And the weight of the bag is W. Okay, so these are 4 objects, and for each object there will be a different weights. So W1, W2, W3, W4. Okay, in order to avoid the confusion, let us take the capacity of bag. Capacity is represented as M, some M. Okay. So there is a one bag or one container with a capacity M, and here in order to move these weights into the bag and carry towards somewhere, it requires some profits. So P1, P2, P3, P4. So with this particular X1 we'll get a profit P1, with object X2 we'll get a profit P2, X3, P3 and X4, P4. Here the problem is we have to arrange the weights into this particular bag that should not exceed the maximum size, and we need to get the maximum profit. That is the problem. And why we are calling it as 0 and 1 means here 0 indicates no move or no insertion. That means we are not supposed to move the weight into this particular bag, or we are not inserting the particular weight into this bag. And 1 implies move or insertion. Move or insertion. So that means if 1 represents moving the weight into the bag or inserting the weight into the bag. Hope you understood the problem. And why 0, 1? So there will be only 2 solutions, either 0 or 1 for every weight. Okay, so this will be 0 or 1, and this will be 0 or 1, and this object will be 0 or 1, and this object will be 0 or 1. So this is a solution, 0 or 1. These are objects, these are weights, and these are profits. Okay, so we need to fill the objects into this bag so that we need to get a highest profit. And for that, moving or not moving is represented with 0 or 1. So that's why we call it as a knapsack problem. Knapsack problem. Right? So in order to solve this knapsack problem, we are supposed to have the 4 things. One is number of objects. Second one, profits, weights, capacity of sack or bag, right? So these 4 things we require, right? So if you are having these 4 things, we can easily find out which objects should be moved from outside to the inside, and by representing with 0 and 1. So now we'll see an example, right? One example, so that you will be understanding exactly how to solve this knapsack problem. Right. Now let us take an example. See, example, let us take objects n as a 4 and capacity as 10. Okay, the sack capacity is 10, and then profits is equal to, so 10, 40, 30 and 50. And weights, what are the weights? So 5, 4, 6 and 3. Okay, so we need to find out which objects should be inserted into the sack so that the capacity should not reach the capacity, go beyond the capacity, right? So for example, here the sack capacity is 10, right? So we can move 5 and 4, the combination 5 and 4, and similarly 6 and 4, and similarly 6 and 3. Okay, similarly 3 and 4. For example, if you go with 3, 4, 5, what happens? The total weight becomes 7 plus 5, 12. So which is beyond 10. So we can't insert the weight, 12 kg weight objects into 10 kg bag. That's the only logic, right? So we need to insert the objects that should not be on the weight. So 10 here, the weight is 10. And here you can get the profit, right? If you move the 5 and 4, the total is 9, so it can be accepted. So 5 and 4, it is 50 profit. In order to carry the weights 5 and 4, the profit is 50. What about the 6 and 4? 6 and 4, it's a 70. And 6 and 3, it's a 80. And 3 and 4, it's a 90. So there are different solutions, okay? So we are having a multiple solutions. So from this we have to find out the optimal solution. So here the optimal solution is based upon the constraint of highest profits. So we need to get the highest profit. Now we'll see the procedure how we have to move it. Okay, see, this is a problem and now we'll go with the solution. So let us take first one, the solution. Okay, the sack S of 0. So we are having 4 elements. So we need to find out 0, 1, 2, 3, 4. That means initially S0 is empty. That means without any weights. S1 means insertion of one weight, of weight 1. S2 insertion of weight 1 comma weight 2. Already weight 1 is there, so we are moving another weight. S3 insertion of weight 1, weight 2, weight 3. S4 insertion of weight 1, weight 2, weight 3 and weight 4. That means here we can say S0 comma W1, and here we can say S1 comma W2, and here we can say S2 comma W3. Here you can say S4 comma W4, because S1 is empty. So empty, we are adding W1, and here W1 and W2. W1 means nothing but S1. So S1 comma S2. Here W1, W2 and W3. S1 is having W1 and W2. So adding third one, right? Now we have to find out all these things, right? So first S0, that means empty stack. So we are not moving anything, right? 0, 0. So here we are representing as PI and WI pair, a profit and weight, corresponding weight. PI and WI, profit and weight. So 10, 5, 40, 4, 30, 6 and 50, 3. So if you want to move 5, you will get a profit of 10. If you move 4, you will get a profit of 40. If you move 6, you will get a profit of 30. If you move 3, you will get a profit of 50. So we are representing this profit and weight as a pair, PI and WI. So initially, so everything will represent in terms of set. Set means nothing but a collection of pairs here. Okay. So initially S0, that's a empty stack. Initial stack, it is an empty. Now what happens? We have to insert 1 into 0th stack. Okay. So we are inserting this one. So obviously insertion means what we are doing? We are moving 5 to the stack with a profit 10. So 0 plus 10, comma 0 plus 5, 5. Okay, we have inserted. Now what is a S1? S1 will be, what is S1? S0 and W1. So S1 means, S0 means 0, 0. W1 means after insertion of one thing. So we are getting 10 and 5. So this is a S1. Remember this one. And this is S0. This is S0. Again, after that, what we have to do? We have to insert one more element, right? Now, S1 and insert one element. So just remember the prefix. Okay, the upper script will be the 1 and lower script will be the insertion of one element. So what we have to do? We have to add one more element. So one more element means 4 with a 40. What happens here? If you add 4, okay, if you add 4 and it is 40, what happens? So complete it is 9 and complete it is 50. Okay, the same thing apply to the S1. So S1, insert to S1. So what happens? 40 and 4. 40, 4. Because we are adding to this particular S1. 0 plus 40 and 0 plus 4. Comma. Then combination. 40 plus 10. 50. Comma. 4 plus 5. 9. 9. So you got it. So empty. Initially we have moved it. And then we are getting the next one. Now, what is a S2? S2 is equal to, so what is a S2 here? So complete S1 and new thing. So S1 is here 0, 0, 10, 5, 40, 4, 50, 9. Right? Yes. Okay. Now you observe what it means. 0 weight, 0 profit. Okay, 0 profit with 0 weight. And if the weight 5, here we are having weight 5. How much profit we are getting? 10. Good. Second case. Adding weight 4. And profit is 40. So you are getting less profit with one weight, because you can see with the weight 5 we are getting only 10 profit. With weight 4 we are getting more profit. So imagine it as a cages. For 5 cages the profit is 10. For 4 cages itself the profit is 40. So which one is better? Obviously this one is better. So we can avoid this particular case. Okay, this rule we call it as a dominance rule. Okay, dominance rule. Dominance rule. That means if Pi is greater than Pj and Wi is less than Wj, less than or equal to, okay, or simply you can write it less than, okay, then we need to remove the pair with less profit. So this process we call it as a dominance rule. Here the same thing happens. Consider Pi and Wi, Pj and Wj. See, Pi, Wi, Pj, Wj. What happens? Pi is greater than, sorry, I have written small, right? Pj and I, and here also J and I, right? So increasing of weight should increase the profit. So Pj is greater than Pi, Pj is greater than Pi, perfect. And Wj is less than Wi, Wj is less than Wi. So we need to remove the pair with less profit. Which is having the less profit? 10 is a less profit, because the pair is profit and weight, not weight and profit. Don't get confused. Okay, profit and weight. The first term will be the profit, the second term is the weight. So if we need to remove the pair with the less profit, that is a 10. So this is also called as a purging rule. Purging means removing, also known as a purging. Okay, so what we have to do in this case? We have to avoid this one. Okay, so now we can write the final S2 0, 0, 40, 4, 50, 9. Okay, only 3 terms we are getting. So 0, 0, 10, 5, 44, 59. So 10, 5 we are removing. So only 3 terms are there for S2. Now find out the next term, that is S3. So in order to find out S3, we need to add 1 to S2. 1 to S2. So the next term is 30, 60. So 30, 60, sorry, 30, 6. And add 30, 6 here. How much? 70, 10. And here 80, 15. Okay. Now you observe the profit is 80 if the weight is 15. That's good. But the maximum weight here is only 10. So in the 10 capacity bag we can't insert the 15 weight. So this is also invalid. So we need to remove that one. Now S3 will be the combination of S2 and the insertion. So consider 0, 0, 40, 4. So before 44 we can get a 30, 6, 40, 4, 50, 9 and 70, 10. So these are the elements. And now again you can see the same thing. So here 6 and here 4. So we are getting a profit for 6 weight 30 and we are getting a more profit for weight 4. So we can remove the less profit. And see 0, 4, 4 to 9 and 9 to 10, 0 to 40, 40 to 50, 50 to 70, everything is okay. Now S3, the final S3, 0, 0, 40, 4, 50, 9, 70, 10. This is the S3. This is the S3. Now insert the last one. Already we have inserted the three things. We need to go with the fourth one. So S1 into 3. So we have to add the fourth one. So 50, 3. So 50, 3. 53. So 90, 7. 53. 53. 100, 12. 50. 120, 13. Right? Okay. Now you can observe this is a beyond the weight 12. So we can't process this one. And this is also beyond weight because 13 and the maximum capacity will also only 10. So you can avoid this one. Okay. Now write on the S4. What is the S4? Combine both the things. S3. So 0, 0. 40, 4. And you can go with the 50, 3. 50, 9. 70, 10. 90, 7. See, these are the S4. And again you can observe, yes, so we are getting 3 with the 50 and 9 with the 50. Weight 3 with a profit 50. Weight 9 with a profit 50. So you can avoid this one. Okay, with only weight 3 we can get a 50, right? So we can avoid this one. So finally write the S4. 0, 0. 44. 50 and 3. 70 and 10, 90 and 7. And again observe, so with 4 we are getting 40 and with 3 we are getting 50. Okay, again there is a violation, the same dominance rule, right? So avoid the less profit. So you can avoid this one. Again write on the final thing. So hope you are understanding. 50, 3. 70, 10, 90, 7. And again you can see, so with 10 weight we are getting 70, with 7 weight we are getting 90. So again there is a problem. So you can avoid this one also. So S4, 0, 0, 53, 97. So this is finally the S4. Okay, so now we found that S1, S2, S3 and S4. So we have inserted all the 4 elements, right? Now we'll see which one is the best. Which one is the best among all these 3? So here the highest is this one. So just consider the same thing. So 90, 7. Check the conditions, belongs to S4 and 90, 7 belongs to S3. Check both the condition. Okay, which one is true? So 90, 7 it is available in S4. Right. 90, 7 is available in S3. It doesn't belongs in S3. Okay. So here you can see it is in S4, not in S3. That means you can simply say that X4 is equal to 1. That means we can move the element into bag, into the sack. Okay, If both are equal, we need not move it. Okay, both are equal. That means if 90,7 belongs to S4 and 90,7 belongs to S3, then we need not move the weight to the stack. So here one condition is true, another condition is false. So move the fourth element, last element or last weight into the stack. Now remove the fourth element from this particular weight. So 90 minus 50 comma 7 minus 3. So this is the fourth one, 50 comma 3. So remove the things from the pair. So obviously it will be 40 and 4. Check out. So 40 and 4. Check the same conditions. Now already S4 completed, belongs to S3, and 40 comma 4 belongs to S2. Check out whether 40 comma 4 belongs to S3. 40 comma 4, it is available, right? 40 comma 4 in S2. Where is S2? 40 comma 4 in S2. Yes. So obviously we can say the third object need not be moved because both the conditions are true. So in both the cases, in both the sets, 40 comma 4 is available, so need not change. So in our first discussions, we say that 1 represents moving the sack into the, moving the weight into the sack. And coming to the 0 representation, we should not move the weight into the sack. Then, so we need not remove the third element from the here. Okay, so simply continue with the same thing. So 4 comma 4 belongs to S2, 40 comma 4 belongs to S1. Check out, in S2, 40 comma 4, it is available. 40 comma 4 in S1, no, not available. So that implies X2 should be moved. X2 should be moved into the sack. Hope you understood. If both the conditions are true, that means if the pair is available in S of I and S of I plus 1, or sorry, S of I minus 1, then no need to move the weight into the sack. So we need to compare each and every set. Okay, so here 40 comma 4 is available in S2 and 40 comma 4 is not available in S1. So that's why we have to move the second weight because we are checking with the second one, right? Now what happens? So here we need to remove the second element from this pair. So what is the second element? 40 comma 4. So 40 comma 40 and comma 4 comma 4. So what happens? 0 0. So it is 0 comma 0. So we have to check again with 1 and 0 comma 0 with S0. So 1 0 comma 0, yes, and S0 0 comma 0, yes. So obviously X1 will be 0 because the pair is available in both the set S1 and S0. So the solution is 0 comma 1 comma 0 comma 1. So the solution will be either 0 or 1, right? So 0 means we should not move the first weight. 1 means we have to move the second weight. 0 means we should not move the third weight. Okay, and 1 means again we have to move the fourth weight. Just observe moving of, see, this is a weight, this is a weight. Moving of second one, second weight is 4 with a profit of 40. Next, third, fourth means this one. Third weight, okay, with a profit of 50. How much total profit we got? 90 profit. So by moving a 3 and 4, okay, by moving a weights 3 and 4, we got a 90 profit. That is a maximum profit. You can check. So 5 4, it's 50. 4 6, it's 70. 6 3, it's 80. 3 4, it's 90. Just now we got it. 5 3, 60. In every combination you can check. So only we'll get a maximum profit if you move the third weight and the fourth weight, the weight 4 and weight 3, that means the second and fourth one. So x2 and x4, if you move the x2 and x4 weights into the sack, then only we'll get the maximum profit. Okay, so this is how we can solve the knapsack problem. So first we have discussed about what is a knapsack, right? And then we have discussed how to solve it. This is by using the set method. By using the sets, we are using all the combinations, and then we are getting the result with the zeros or ones, which are to be moved and which are not to be moved. So once again, I am repeating. So initially insert one element, and then initially the sack will be 0, and insert one element and combine both the things, and insert the second element and combine both the things, and just remember, so make it a mark of S0, S1, S2, S3 and S4. And one thing we have to remember, the dominance rule: if the Pj greater than Pi and Wj less than Wi, then immediately remove the pair with the less profit. Simple example, we are inserting weight 5 and we are getting a profit of 10, and we are inserting weight 4 and we are getting a profit of 40. So here the remaining weight we can insert into a bag is only 5, and in this case we can insert the weight of 6 into the bag, right? So that means with the highest weight we are getting a lowest profit. So such cases we can remove the pair with low profit, and that we call it as a dominance rule, or the technique called a purging mechanism. And one more thing, so if the weight exceeds the maximum size, then also we can remove the pair. Here you can see 80, 15. So 15 is the weight which is beyond the maximum. So we have avoided it, we have ignored. So here in this case at 12 and 13 we have ignored, right? And all these are the purging. Okay, so dominance rule, applying the dominance rule. Afterwards we need to check the highest weight or highest profit pair with the S4 and S3, so that if it belongs to in both the cases, simply we can say we should not move it, because already in either cases, in some other case it may be available. So automatically we should not accept it if the pair is available in Si and Si minus 1. And if not, then immediately we can move that particular weight, and we have to remove the fourth, that particular weight and profit from this particular weight, profit and weight pair. Right? So like that, finally we will get the solution in either only zeros or ones. So this represents we are moving. So by moving the second object and a fourth object, we will get the highest profit. By moving the second object 4 and fourth object 3, we are getting the maximum profit of 90 rupees. So 90, profit as 90. Okay, so this is how we can solve the 0-1 knapsack problem. Right? So hope you enjoyed and hope you understood the thing. So just practice a few more so that you will be confident about solving this 0-1 knapsack problem. Right? So let's stop here. If you are having any doubts regarding this procedure, so feel free to post your doubts in the comment section. Definitely I will try to clarify all your doubts. If you really enjoyed my session, like my session, share my session with your friends, and don't forget to subscribe to our channel. Thanks for watching. Thank you very much. Hello friends, welcome back to our channel. So today we will see one more example for knapsack problem. So in our previous session we have seen what is a knapsack problem, and then we have solved one problem, right? Now we will see one more problem. So we need to take a number of objects and corresponding weights and corresponding profits, and also the weight, the maximum weight of a sack, right? So let us take 3 objects. So x1, x2, x3, and the profits. So some 35, 40 and 30, and the corresponding weights. let it be 10, 25 and 20. And the maximum sack weight is 40. Maximum sack weight is 40. Now we need to find which object should be inserted into a sack so that we will get the maximum profit. Okay, now let us assume the sack is empty. So S of 0, it will be 0, 0. And after considering the empty sack, just insert the first object. So I am inserting one object to the empty sack. So we need to add the first profit and weight to this one, right? So these are nothing but profit and weight pairs. The pair is profit and weight. So why I am writing like this means the first element is a profit and the second element is a corresponding weight. So 35 plus 0, it's a 35, and 10 plus 0, it's 10. Now with one element, that means with one object, the sack with one object is the empty sack and after insertion of one object. So this is a S1. So we need to note down these things. This is S1 and this is S0, which is an empty sack. Now I am inserting one more object to sack with one object, right? So add the second one, 40 and 25 to 0, 0. It is 40, 25. And 40, 25 to this one, right? 40 means 75. Next 25 plus 10, it is a 35. So you can see it is in an increasing order, right? There is no dominance. So with a weight of 25 we are getting 45, and with a weight of 35 we are getting some 75. So there is an increase. There is no problem. And S2 is, so combine both these things, 0, 0. So 35, 10, and after insertion, so 45, 25 and 75, 35. Right? Now this is the S2. So we have taken three elements or three objects. So we need to calculate the S0, S1, S2 and S3, because already two elements or two objects have been inserted into a sack. Now the third one. So after insertion of 1 in sack 2. So what is the third one? 30, 20. So 30 plus 0, 20 plus 0. So 30, 20. 30, 20. So 65, 20 means 30. 30, 20. So 75, 20 means 45. 30. So 105 profit, 20. It's a 55. It's a 55. Right. Now you can eliminate these two things because the maximum weight is a 40. The sack can accept up to 40, right? But here we are having some 45 and 55, which is beyond the maximum weight, so we can avoid these things. And now we can consider only these terms, that is S3, so 0, 0 and 30, 20. 30, 20, next 35 and 10, 45, 25, 65, 30, 75, 35. And here you can see with the 20 weight we are getting some 30 profit, and here with 10 weight, we are getting 35 profit. So which is a dominance, right? Which is a dominance. So with a less weight, we are getting more profit. So what we have to do? So we can simply avoid the pair with less profit. So among these two, the less profit is 30. So we can simply avoid this set or this element, right? Now we'll write the pair. S3 is equal to, what are the pair? So 0, 0, 35. See, you can observe 35, any other deviations, dominance here. So 35, 10, 45, 20. So both are maximum and here also maximum. 45, 65, 25, 30 maximum. 65, 75, 30, 35 maximum. So there is no dominance, right? So 0, 0, 35, 10, 45, 25, 65, 30, 75, 35. So among these one, so we can see this is the maximum profit. We can get a maximum profit. Now we'll go with this one. So checking out 75, 35, which belongs to S3, and 75, 35 belongs to S2. So let us check. S3, 75, 35 belongs to S3, true, and 75, 35 belongs to S2. So whether there is a 75, 35 and S2, yes, it is there, right? So there is no change, we need not change. And the third element cannot be inserted into a sack. Third element cannot be inserted into sack. After that, we have to remove, so we need not remove it, okay, because in both the things we are having the same thing. So 35 belongs to S2 and 75, 35 belongs to S1. Let us check. S2, yes, it is available. S1, there is no. So there is no. So there is a deviation. Obviously we can say X2 should be inserted. X2 must be inserted because in S2 it is there, in S1 it is not there. Now what happens? We have to remove the second object, second object profit and weight with this one. So 40, that means a 35, 10. Check it out, S1 and 35, 10 belongs to S0. So we need to check only in two sets. One is S power I and the next one is S power I minus 1. Okay. So 35, 10 it's available in S1, right? Yeah, 35, 10 is not available in S0. So obviously we can move the first object into sack. First object into sack. So you can say the solution S is equal to 1, 1, 0. That means inside the sack we are supposed to move the first object and second object so that we'll get the highest profit. So what is the first object and second object? 10 weight and 25 weight. 10 plus 25. So what is the profit here? We are getting 35 plus 40, which is 75. Okay, so let us check more. Okay, so if you move 25 and 20, that means second object and third object, we can't move because the weight goes beyond the maximum size, right? So we can go with x1 plus x3. So 10 plus 20, the profit will be 65. Okay, so there is no chance. So obviously with this move we can get a more profit. That means moving the objects x1 and x2 into the sack will get a maximum profit, right? So hope you understood this simple problem So still, if you are having any queries regarding this problem, so feel free to post your doubts in the comment section. Definitely I will try to clarify all your doubts. And if you really enjoyed my session, like my session, share my session with your friends, and don't forget to subscribe to our channel. Thanks for watching. Thank you very much. Hello friends, welcome back to our channel. So today we'll see one more concept in a dynamic programming in algorithms, that is a traveling salesman problem. So this problem will solve by using the dynamic programming method. So in our previous session we have already seen what is a dynamic programming, right? So a complex problem will be divided into subproblems, and each subproblem will be solved, and the solution of each subproblem will be saved in the memory, so that in future, in order to avoid the recalculation, so we'll make use of the existing solutions. And this is also mainly used to solve the optimization problems, where there will be a lot of solutions. Among them, we have to select the optimal solution based upon the given constraint. So this is about the dynamic programming. So about all this dynamic programming we have seen in our previous sessions. So I'll post the link in the description. So just go through. And now we'll see what is a traveling salesman problem. So here, first let us see what is this problem. So there will be a graph. So here we are supposed to take a graph. Okay, so consider different vertices and edges. We know that a graph will be having vertices and edges. So how this graph is related to our salesman problem? So consider the edges as a distance and vertices as a places in the city. So how the salesperson travels from one place to another place, covering all the places in the city with a minimum distance. Okay, so assume each vertex as a place in the city, so that from the source, the salesperson should start traveling and have to visit all the places only once. Okay, all the places only once, and have to come back to the source. So this is the salesman problem. That's also with a low cost. That means distance, least distance. So for that relation, we are taking the complete places as a vertices and the distance as a edges, so that we can have a graph and we can solve it. So one thing, we have to select a source. So selection of source. That's the first important point. And the second one, so starting from source, traverse through all vertices in a graph exactly by one time, and come back to source with minimum distance or cost. Minimum distance or cost. So we have to select the source node, and from that source node we have to traverse all the vertices exactly one time and come back to the source with a minimum distance or cost. So for this we have to consider a weighted graph. So every edge should have a weight which represents the distance or a cost, whatever it may be. Okay, so we have to consider weighted graph. And one more important, so we can have the directed graph or undirected graph. So graph can be directed or undirected. So I think you know the difference between this directed and undirected. Okay, for example, if A, B, C, and this is a graph. Okay, this is a graph. So there is no directions on the edges. So this comes under undirected. Undirected. For example, A, B, C. Okay, so there is a directions. So there is a direction. That means this edge is between A and B. This edge is between B and C. This edge is between C and A, right? So there is a directions. So this is a directed graph. So we can work this problem, traveling salesman problem, either on both directed or undirected, but it should be a weighted graph. So for every edge there should be a weight, okay, which represents the distance or a cost. And one more important point is the graph, either directed or undirected, the graph should be complete graph. Complete graph. So what do you mean by complete graph? So every vertex should have the edge to all other vertices. Okay, for example, consider A, B, and C. So this is an undirected graph. So we can say this is an edge between A and B and also B and A. For example, let us take the distance. So this implies the distance between A and B is 10. Similarly, the distance between B and A is also 10. Distance between A and C is 20. Similarly, C and A also 20 because undirected. So if it is like this, A to B, B to C, C to A. So this is also an directed graph, but not a complete graph, because A is having an edge from A to B. There is no edge for A to C. And B is having an edge for B to C. There is no edge for A. C is having an edge for A. There is no edge for B. So the complete graph means every vertex should have the edges towards all other vertices. For example, so A is here. I will write one more edge here. So A is having edges to B and C. Now B is having only for C. I will write here. So B is also having an edge from A and C towards A and C. So C is having only for A. So C is also having an edge to A and B. So A is having edge to B and C. B is having an edge to A and C. C is having an edge to B and A. So this is the complete graph. This is the complete graph. Complete directed weighted graph. Okay, so this is a complete weighted, complete directed weighted graph. Okay, so in such type of graphs, we can apply this traveling salesman problem. Okay, so these points are most important before starting the problem, right? So selection of a source, we can select any vertex as a source, but from that particular vertex, we have to traverse all other vertices exactly once and come back to the same vertex. And consider a weighted graph, so that should be a weighted. Graph can be a directed and undirected. Graph should be a complete graph. So these points are most important. Right. Now, so before going to this one, let us have a formula. So just remember the formula, so that while solving the problem, you can understand the formula exactly, right? So here we'll write a formula. the function I comma set. S stands for set, which contains a number of elements, or we can say vertex, right, is equal to cost of I comma j. So j, so here, okay, I'll write here itself. I'll erase this one. I'll write here. So g of I comma set, which contains all other vertices, is equal to minimum of j belongs to set cost of I j plus again a function j comma set minus j. So this is a formula which we have to remember while solving the problem. And one more formula, g of I comma pi is equal to cost of I comma source. I comma source. Okay, right. And one more thing, remember one more thing, cost of I comma j will becomes 0 if I equal to j, and becomes cost of ij if ij edge belongs to graph. Ij belongs to graph. That means if there is an edge between I and j. Okay. So just remember the cost, if I and j both are equal, then the cost will be 0. Right? Yes. Otherwise we can write down the direct. So remember this formula. So we need to calculate the shortest path from source, visiting all vertices, and come back to the source. Right. So I is a source. Okay, I is a source, and S is a set of all vertices. Other than I. Okay. From that we have to find out the minimum. Okay. So we'll write down the example. So let us take this example. Okay. So this is a undirected graph. Okay. First let us check. It is an undirected graph. This is a weighted graph because for every edge there is a weight. And let us check whether it is a complete graph or not. So here we are having a 4 nodes, that means a 4 vertices. So every vertex should have the 3 outgoing edges. So A is having an edge from A to B, D and C, right? From B to A, B to D, B to C, okay? C to B, C to D and C to A, okay? D to A, D to B, D to C, yes. So this graph is a complete weighted undirected graph. Now we have to solve the problem. First let us write down the table. Okay, let us write the adjacency matrix. So I am writing here. So A, B, C and D, and here also A, B, C and D. So we'll write the cost. Okay, so this is I and this is J. So there will be no edge from A to A or B to B or C to C or D to D. So that's why I have mentioned. So cost of I comma j will be 0 if I is equal to j. So if I is equal to j, then the cost will be 0. And it will be Cij if the edge ij belongs to graph. Okay, see, A to A. So I is equal to A, j is equal to A. Obviously it will be 0. Next, A to B. Then if there is an edge, A to B, yes, there is an edge. So belongs to graph. Okay, A comma B belongs to graph. So that implies the cost is 10. Next, A to C, 15. A to D, 20. Similarly, B to A is 10, B to B there is 0, B to C is 35, B to D it's a 25. Similarly, C to C again it's 0, C to B it's 35, C to C 0, C to D it's a 30. Similarly, D to A it's 20, D to B is 25, D to C it's 30 and it is 0. Okay, sorry, C to A 15, it's not 0, C to A it's 15. Right. So this is an adjacency matrix. Okay, so this represents a cost from one edge to another edges. It's clear. Now, so just start with the set 0. Okay, if the set contains 0, what are the different possibilities? If set contains one element, what are the different possibilities, different edges? Now, we'll select the source. So, I'll write source as A. A is a source. Okay, A is a source vertex. Now, first, if set is equal to 0, okay, the set contains different elements. Okay, so 0th element, first 1 element, 2 element, 3 elements, because the source is A. So if set is equal to 0, apply the formula G of I means B. So from B, comma, set is 0, there is no element, so that can be represented as pi. If set is equal to 0, then we can represent it as pi. Now what happens? See, if I 0, then I comma source. So this will be G of, what is I here? B, comma, what is the source? A. So what is the cost here? B to A, it is a 10. Similarly, there is a possibility of C to pi. C with no element. So G of C comma source, which is nothing but C to A, it's a 15. Similarly, G of D comma pi, G of D comma A, which is DA, it's a 20. So which means if the last vertex is B, obviously our statement says that we have to visit all the vertices and come back to source. So that's what happens. So if the last vertex is B, then what is the edge from B to source? And if the last vertex is C to A, that means, for example I am saying A is here, the next edge can be B, C and D. From this, if B, the next edge can be C and D. Next edge can be B, D. Next edge can be B, C. And A, B, C, obviously it will be D. A, B, D, obviously it will be C. If A, C, B, it's D. A, C, D, it's B. A, D, B, it's C. A, D, C, it's B. So only one vertex. So all the vertices have been visited, right? So this is a possibility, maximum possibilities, all possibilities. So after coming to D, what's the next move? So visited all vertices here. So it should go back to A. Similarly, if it is C, it should go back to A. If it is D, again it should go back to A. B, go back to A. C, it should go back to A. B, it should go back to A. So that's what here we have written. If B with a null set, that means no other vertices are remaining to visit, then obviously the next move will be from B to A. And that means at this position, if there are no unvisited vertices, if set is 0, no unvisited vertices. Obviously the edge should be towards the source. So that's why we have written this formula. I comma pi, then I comma source. Right? So hope you understood this one. And the next possibility. So only 3 possibilities because we are having 4 edges, 4 vertices A, B, C, D, and here we have taken source as A. So we need to check the possibilities of all the remaining 3, B, C, D. Right? Now, if set is equal to 1, that means if there is only one unvisited edge, unvisited vertex. If the set contains unvisited vertex, only one unvisited vertex, then possibilities G of B and the unvisited from B, where it can go, either it can go to D or B, it can go to C. Only 2 possibilities. Okay, only 2 possibilities. So if there are one more vertex, for example, if there is one more vertex, then we can write it here G, B comma E. That means there can be edge between B and D, B and C, P and E. So anything, right? So the set contains 1 means having one unvisited edge, vertex. So always I am getting edge, right? So that's a vertex. Okay. So write down the formula here, B, D. So what is the minimum of J belongs to S? Here J means D. D belongs to set S. So Cij, that means C, B, D plus G of J comma set minus J. J here D, D comma set minus D. So here set is nothing but D. See, here set is nothing but D. So D minus D, obviously it will be empty, right? So empty means we can simply write it here, pi. Okay, so there is no other edge, only one edge is here. So only one unvisited vertex. So we are just getting the cost of that particular unvisited vertex. So if there are multiple, obviously we can have to select the minimum edge. So here we are having only one thing, so we can simply remove it and we can write it C edge BD plus G of D comma phi. Okay, so you can see what we have done in the dynamic programming. So we are dividing the complex problem into sub-problems and we are calculating each sub-problem and we are storing in the memory. So that's what we are doing. So here G of D comma phi we need not recompute it. So already we have recomputed. So D comma phi is this one. So obviously we can get the value from here. So CBD plus G of D comma phi, which means cost of B and D, it's a 25 plus 20 D comma phi. So which is 45. Now again G of another possibility. So there can be an edge from B to C. So this can also be written as BC plus G of, so what is the J here? C comma set minus C. Obviously it will be pi. So the edge between B and C, BC 35 plus G of C pi, it's a 15. So which will be 50. So here we have taken B as a source and we are computing the cost between B and all unvisited edges. See here, next change it, C to B. We can check the possibility. If C is a node and we have to check from C to all possible unvisited vertices. So C to B, and similar here, CB plus G of B comma set B minus B. So obviously this pi. So which will be CB 35 plus G of B 5 10, which is 45. And similarly from C there might be having an edge to D. Okay, C to B. Okay, now C to D. Cost of CD plus G of D comma pi. So cost of C comma D, C to D is 30 plus D pi 20. So which is 50. Hope you understood. If set is equal to 1, we need to, the set is 1 means 1 unvisited vertex. There is a one unvisited vertex. Okay, so we need to check all the possibilities towards that unvisited vertex, right? So if you consider B, B to D and B to C. If you consider C, C to B and C to D, because we are having only 4 vertices. So if our graph is having the 5th vertex, so here we will get one more thing, G of B comma E. Okay, that's also one possibility. The same thing, right? Now, consider set is equal to 2. That means 2 unvisited vertices. Unvisited vertices. Here also we have to go with the different possibilities. Check it. G of B, consider B as a source. From source, 2 unvisited vertices will be either C comma D. Okay, C comma D, unvisited vertices. So how we can write it here? Here we can write minimum of, okay, first cost of BC and cost of BD plus G of, what happens here, C comma, okay, set C comma D minus J C plus G of D comma C comma D minus D. So among these two we have to find out the minimum from this formula only, right? J belongs to S, C, I, J. So C, D are the 2 elements in the set. So BC and BD. So in this case, J value is C. So G of J value C comma set C comma D minus J minus C. And in this case, J value is D. So plus G of D comma C comma D set minus D. So obviously you can see set C comma D minus C means it will be D. Okay, and here C minus D means it will be C. Hope you understood. So among these two, we have to select the minimum. So that's the formula. And in the previous case, we are having a set with only one element. Okay, only one unvisited node. So we are having only an edge between B and D, B and C, C and B and C and D. Now we are having 2 unvisited vertices. We are having 2 unvisited vertices. So there can be a chance of having an edge between B to C and B to D. B to C and B to D. So among those we have to select the minimum cost. So that's why minimum BC plus this one. And here, and this will be BC 35 plus G of C comma D. Already this was calculated here. C comma D, which is 50. So which is 50, 85. And coming to this one, C of BD 25 plus DC. Already we have calculated here. Oh, we have missed it. Yes, we missed it. I'll write here G of D comma C. So we have missed it. We have calculated till CD. So for D also we have to calculate, and DC. So C of DC plus G of C comma 5. So which is DC 30 plus C pi 15 is equal to 45. There is one more possibility. From D there can be a chance of edge to B. So this is one more chance, right? So C of dB, that means the cost of dB plus G of B comma 5, similar to this one, right? Similar to this one. So what is the cost here? dB. So D to B 25 plus G of B pi. G of B comma pi. Okay. So G of B pi 10, which is 35. Which is 35. Right? I'm sorry, the board is very small, so I'm forcibly adjusting everything in the single board, right? Okay, just right. Now here you can get cost. G of D comma C. D comma C cost is 45. So which is equal to 70. So which one is the minimum? 70 is the minimum. So you have to consider this one. Okay. Now again G of, if C is the source, what are the remaining elements? B and D. So minimum of CB, CD plus G of B comma, okay, from set we have to minus B, so obviously it will be D plus G of D comma B. So which is cost of CB it's a 35 plus G of B comma D, G of B comma D, which is 45. It's a 980. Okay, and this one CD, C to D 30 plus DB, here we have written DB 35, so which is equal to 65. So among these two, which is minimum? 65 is the minimum. So this we have to consider. And the next one, G of, what is the next? D. If the possible source is D, from D there can be edge between B and C. So here we can write B and C is equal to minimum of CDB CDC plus G of B comma, from set we have, if you minus B, the set will be containing only C, plus G of, if C is a source, and remain minus C from the set, so it will be B. So what is the amount here? Cost of DB is a 25 plus BC cost is 50, 75, and here what is the cost here? D to C 30 plus CB, which is a 45, again it is a 75. So both the edges will be having the same cost, so we can select any one edge, no problem. Okay, so only possibilities, 3 possibilities we have chosen, right? If the source is B, there can be edge from B to C or B to D. If the source is C, there can be edge between C to B or C to D. If the source is D, from D there can be a source to B or C. Now, if set contains 3 elements, that means 3 unvisited 3 unvisited nodes. So G of, here 3 unvisited means the source A, B, C and D, because here we are having only 4, right? Among 4, the 3 are unvisited, and obviously the next one will be the source. So I'll write here, so which will be a minimum of C of AB, C of AC, C of AD plus G of B comma, if you subtract B from set, it will be C comma D plus G of C comma BD plus G of D comma BC. Okay, hope you understood this formula. So J comma, from set we have to subtract the J value. Okay, so here J value is B, we are taking B from set, so CD. Here J value is C, we are taking C from set, so it will be BD. Here D is a J value, so we are taking D from set, so it will be BC. Okay, so calculate the cost. CAB, so AB cost is 10 plus B of CD. So here we have calculated, and here we are having a 2 values. Among these we have to select the minimum, so 70, so which is 80, and the next one AC, A to C, it's a 15 plus CBD. Here also we have calculated 2 values, 80 and 65. So among these we have to select the minimum 65. So it is also 65 and the result is 80. And the third one, AD, cost of AD is 20. D of BC, which is both are same value, so we can select any value. So it is 75, which is a 95. So among these 3, we have to select the minimum, and see, we have to stop the process because we are having a maximum of 4 nodes or 4 vertices, and among these the 3 are unvisited. So already we have fixed that one as a source, and only the possible are 3 more vertices, and we have repeated from 0 unvisited to 3 unvisited. So we have to stop here, right? Now among these we can select the minimum, but here you can see we are having 2 possibilities because 2 values are same, 80, 80, and we can't select this one because it is the highest. So we have to select either this node and this node. So the path, the possible solutions are A to B or A to C. So A to B or A to C. Okay, then first if it is A to B, the next one is B, C, D. Go to here, B, C, D here. So among these we have selected this one, right? So this one we have selected, B to D. Now B to D. And coming to this one, A to C. If A to C is one edge, then next to CBD, CBD. Among these we have selected the minimum, that is CD. So the next vertex we visit is D. Now if D, okay, this one we have selected. Next D comma C. Go to that thing, D comma C, this one, D comma C. So the cost is DC. The next one will be C. And similarly here also go to CD, DB. So DB means here. So after that the next node will be B. And after that, in both the cases, the next vertex will be A. So that implies there are 2 possible paths where starting from A, visiting first vertex as B, next D, followed by C, and come back to A. This is one possible path with a distance of 80. So you can calculate A to B, which is 10, B to D, which is 25, D to C, which is 30, and again C to A, which is 15. Total we will get 80. And similarly here, starting from source A, visiting first vertex as C, next vertex as D, followed by B, and come back to A. So in both the cases, the distance is 80. So there are two possible paths. So if we are having only one among these three are minimum, so that will be the single path where the person can travel from source to visiting all vertices and come back to the source. So here we are just calculating and we are saving the result and we are making using this result in further procedure. Right? So hope you understood this problem. So one constraint, we have to consider the weighted graph, and we can consider either directed or undirected, and that should be a complete graph. Okay, only two formulas we need to remember, and based upon two formulas we can solve. Starting from 0 unvisited link, 1 unvisited vertex, 2 unvisited vertex, and 3 unvisited vertex. So until n-1 unvisited vertex, we have to calculate this procedure. Right? So hope you understood and enjoyed. So if you are having any doubts regarding this procedure, feel free to post your doubts in the comment section. Definitely I will try to clarify all your doubts. If you really enjoyed my session, like my session, share my session with your friends, and don't forget to subscribe to our channel. Thanks for watching. Thank you very much. Hello friends, welcome back to our channel. So today we will see one more problem in traveling salesman problem. So in our previous session we have seen what is a traveling salesman problem, and we have solved one example which is an undirected complete weighted graph. Now in this session we will see one more example which is weighted directed complete graph. So we have seen the difference between a complete graph and a normal graph, and also weighted graph and unweighted graph, directed and undirected, right? So now we will solve this example, right, by using the dynamic programming. First let us write the adjacency matrix, and we'll erase this one because the board is very short. So I'll write the adjacency matrix and I'll erase the complete thing, right? I'll write the adjacency matrix here. So A, B, C and D. So 4 vertices. So we'll write the cost from one vertices with another one. So A to A, so which is always 0, and A to B. So A to B it is 10, A to C it is 15, A to D it's 8, B to A 5, B to B 0, B to C 13, B to D it's 10, C to A it's 6, C to B it's 9, C to C 0, C to D it's again 9, and D to A it's 20, D to B it's 8, D to C 12, and D to D is 0. So this is the adjacency matrix, right? So I'll erase this one. So which is an weighted directed complete graph. Now first we'll write the formula. So we need to remember two formula before starting the solution, right? So G of I comma set of S is equal to minimum of J belongs to set cost of Ij plus G of J comma set minus J. This is one formula. And another formula, so cost of or G of I comma pi is equal to G of I comma cost of I comma source. So we need to remember these two formula. So before starting the solution, now we need to find the minimum distance from source vertex visiting all other vertices at least once, exactly once, and come back to the source vertex. So we'll see the source vertex as A. So we can consider any vertex as source vertex. So the first step we have seen in our previous session, that is we need to select the source vertex. So here I will select the source vertex as A. Now we need to start from A, visiting all nodes and come back to A with a minimum distance. So we'll write the next possible source, unvisited. So first one, let us take if set is equal to 0. That means no unvisited vertices. If there are no unvisited vertices, then the recent vertex will be the last vertex. So the possibility is g of b comma phi, because itself is the last vertex. So what is the formula of this one? G of I comma phi is a cost of b comma source. Here the source is A, cost of A. B of A, cost of b comma A. So we can write simply it as G of b comma A, which is b to A, it's a phi. Similarly, if the last vertex is C, then obviously if the last vertex is C and there are no unvisited vertices, then immediately we need to reach the source. So that's what the problem. So we need to start from source, visiting all the vertices exactly once and come back to the source. So if the last vertex is C and there are no unvisited vertex, so obviously we need to go to the source. So G of C comma source. So CA, which is a 6. And the next possibility D comma pi is equal to G of D comma source. So it is 20. Okay. So the only possibilities are this one. The only possibilities are this one. Now let us assume if set contains 1. 1 means unvisited vertices 1. So I write here 1 unvisited vertices. 1 unvisited vertex. Okay. So for example, if we are at B and there is only one vertex, so what are the remaining vertex? For example, if we are at B, what is the remaining vertex, unvisited vertex? It may be C or it may be D. For example, if our graph is having one more vertex like this one, B, C, D, E, right? So if our graph is having one more E, then there is a one more possibility E. So we need to check the cost for each and every edge. If B, B to C, B to D, B to E. That means the set contains only one unvisited. Only one unvisited. So if we are at B, the unvisited can be C. And similarly, if we are at B, the unvisited is D. So two possibilities. So we are at B, so unvisited vertex, it may be C or D. So we need to find out this one. So what is the formula? Minimum. So here we are set is having only one element. So we need not write this minimum because we will get only one formula. So C of BC plus function of, what is this one? Consider it as a J. So J, that means C comma G of J comma C comma set of C minus C. Set of C minus C. So this can be written as a pi. So obviously, so we can replace this one. So we are having the set as C. We have to subtract the C itself from the set. So the remaining is pi. Okay. So what is the amount here? What is the cost here? C BC. What is the BC cost? B to C 13 plus G of C comma Yes, this is the thing I have written wrong. So g of c comma pi. Okay, c comma pi. So what is the value of this c pi? Already we have calculated here. So that's what we are saying in the dynamic programming. So the complex problem will be divided into subproblems, and we are solving the subproblem and we are storing the result, so that in future if it is required, so we can make use of the value from the memory. So here already we have calculated, so we need not calculate once again. So we can simply use this value 6. So here 13 plus 6, which is 19. 13 plus 6 is 19. And now let us calculate the second thing. So the next possibility, b comma d. If the unvisited vertex only one is d, then c b d plus g of d comma pi. Because the set is having only d and we need to subtract the same vertex from the set. So which is nothing but pi. And here what's the value? bd, hbd, b and d. It's a 10 plus g of d pi, which is 20. So what is the value here? 30. So we need not select the minimum because only one calculation. This is 1 edge and this is 1 edge. Okay. So this is 19 and this is 30. So now change the vertex. If we are at C, the possibilities are B. Okay. So cost of CB plus G of B comma pi. So which is a cost CB? CB it's 9 plus GB pi. It's a 5, which is 14, which is nothing but 14. And the next possibility, G of C comma D. If the unvisited vertex is D, so cost of CD plus G of D comma pi. So cost of CD, age C D is 9 plus G of D pi 20. 29. Okay, so we have completed the two vertices. Now if the vertex, we are at D, if we are at D, so G of D comma, the possibilities are C, so which is cost of DC plus G of only one element, so C comma pi. So DC it's a 12 plus C pi, which is 6, is equal to 18. And there is a one more possibility. If we are at D, the next unvisited can be B. So C dB plus G of B comma pi. B comma pi. Then see dB. So dB means 8 plus G of B pi, which is a 5. So which is 13. So we have completed all the possibilities if unvisited is one vertex. If unvisited, so just listen carefully. So if the set is having only one unvisited and we are at B, then the possible unvisited vertex will be C and D. And the next possibility, if we are at C, the next unvisited will be either B or D. And if we are at D, the next unvisited will be either C or B. So we are calculating for all the possibilities. Now, so we have calculated all the possibilities if set is equal to 1. Now calculate with set is equal to 2. That means if set is having two unvisited vertex. Two unvisited vertices. Right? Now calculate G of B. Okay. Comma. If the set is, if we are at B, the next two unvisited can be C comma D. Okay, C comma D. So how we can write this one? So G of, we have to write down this formula. So we are having a two possibilities, two edges. One is BC, another one is BD. So among that we have to select the minimum. Okay, so previously in the set we are having only one unvisited vertex. So we need not calculate the minimum because we are having only one edge. There is the possibility of having one edge. But here we are having the in the set two unvisited vertices. So that means there will be a two possible edges. So among those two possible edges, we need to select the minimum one. So how we can write? So G of I'll write here, okay. So minimum of cost of BC, cost of BD. So these two are the possibilities. Plus G of, okay, what's the formula? G of J. Here J is C, comma set minus J. So set minus, here the set is having two elements. So set minus C, obviously it will be D. And here also G of, here J is D. So D, comma set minus D, it will be C. So we need to select the minimum cost among these two. So what is the cost of this one? So BC, okay, BC, B to C, it's 13 plus G of C comma D. Already we have computed this one. G of C comma D. So G of C comma D, which is 29. So this will be 29. So 13 plus 29, right? So that will be 42. Okay. And what about this cost? C of BD. BD. It's a 10 plus G of DC, already calculated. DC, which is 18. So the cost will be 28. So among these two, which one is the minimum? So this is the minimum value. Okay, we need to select that one. And next, so this is the possibility. If we are at B, the next possible edges will be either C and D. Now, G of, if we are at C, the next possible unvisited are B and D. What we have to do? So minimum of cost of CB and cost of CD. And here the J value is B, so B comma, from the set we are removing the B, so the remaining is D. And here it is D, and in the set, from the set we are removing the D, so it will be B. So what is the cost? Cost of CB, what is the CBH? 9. So this is a 9 plus G of B comma D, already we have computed, so BD, so this one 30, which is 39. And what about this one? CD, C to D, it is 9 plus DB, here DB, which is 13, which is 22. Right? So among these two, which is the minimum? This one is the minimum. This one is the minimum. Okay. So among these two, this is the minimum. Among these two, this is the minimum. So if we want to consider the edge, we have to consider this edge. That means C to D. And if you want to consider here the edge is B to D. Okay. Now, so what happens here? Again, check one more possibility. So there is one more possibility. G of, if we are at D, the next possible edges will be B comma C. So how we can write it? So minimum of cost of DB and cost of DC plus G of, here B is a J, and from set remove B, so C. And here also G, the J is C, from set remove the C, so it will be B. Now calculate the cost. DB, so DB, which is 8 plus G of B comma C. G of B comma C, which is 19. which is 27. And what about this cost? DC, D to C, 12 plus G of C comma B. G of C comma B, which is 14. So which is 26. So among this one, this is the minimum. Sorry. This is the minimum. Okay, this is the minimum. So if you want to consider the age, we need to consider D to C. Okay. So here we have completed the set 2. That means set of 2 unvisited vertices. Now we will see set of 3 unvisited vertices. So if S is equal to 3, so 3 unvisited. So what is the possibilities? So so 3 unvisited vertices means B, C, D, because in our graph we are having 4 vertices. Among these 4 vertices, 1 vertex we are considering it as a source, and remaining 3 are the unvisited vertices. So simply here we can write it as source, and in the set B, C, D, all the 3 are unvisited. All the 3 are unvisited. Now what we can do here? So we can write it as minimum of cost of AB, cost of AC, cost of AD plus G of here J is B, so G of B minus set minus J, set minus B. Here the set is having B, C, D. Among that we have to remove the B, so it will be set of C comma D, and here also G of C comma, and here the J value is C. From set we have to remove C, so it will be B comma D, and here also G of J value is D, and we have to remove D from set, so it will be B comma C. Now calculate here, right? So we need to consider the minimum among these 3. So CAB, that means edge AB, A to B, it's 10 plus G of B comma CD. Already we have computed this one. G of B comma CD. Okay, what is the value? So we are having 2 values and we have to consider the minimum. So among these two, 28 is the minimum. So we have to consider 28. So the result is 38. And coming to this one, A to C. So A to C, it is a 15. 15 plus C comma BD, already computed, C comma BD. Here also we got 2 values. Among these 2 we have to consider the minimum. What is the minimum value? 22. So here we need to give 22, which gives 37. And coming to this one, A to D, which is 8 plus G of D comma BC. D comma BC, among these 2 the minimum cost is 26. Consider 26, which is 34. Okay, so among these 3 values, which one is the least? 34 is the least, right? So we have completed this one. There are no other possibilities, because the from source let us consider all the remaining 3 vertices are unvisited. So that also we have computed. So we need to stop here, right? Now we need to find out the path with the minimum distance. So what is the minimum distance among these 3? So only 34. We are getting 34, right? So all the remaining values, that means remaining 37 and 38, both are greater than 34. So here we are having only one path with a minimum cost, that is 34. Now we have to write down the path. So what is the edge of this 34? A comma D. So from source, the next visited vertex is D. Okay, next visited vertex is D, and then we need to find out the next edge from this function GDBC. Go to here, GDBC. Which one we have considered? This one. So from D, next vertex is C. So we have to consider this DC. The next vertex is C, right? And again go to this function for finding the next edge. So from C, next edge, C to B. So go to here, C to B. So edge is C to B. That means B. Okay, B, because here we are having only one value, right? So go to the B to 5. B to 5. The next edge is A. So obviously it will return back to A. So here the cost is 34. So this is the shortest path. Okay, the shortest path means, so minimum distance visiting all the vertex exactly once from the source and coming back to the source. Now we'll see A to D, it is 8. D to C, it is 12. C to B, it's 9. And B to A, it is 5. So you can consider 8 plus 5, 8 plus 12, 20, 29, 29 plus 5, 34. So which is this one? So we need to consider this edge. And from this, we have to consider this one. From this, we have to consider, so C comma B, this one. And from this, we have to consider this one. So these are the edges. So this is the order we have to, the salesperson or the salesman traverse the vertex with a minimum distance. Right? So if you are having 5 vertices, the one more calculation will be there. So this is one more calculation, and after that we'll get the final calculation. So once practice with on any random graph considering more number of vertices, so that you will be getting understandable. So you will be understanding very easily. Right? So be careful while calculating or by performing these additions, because if anything wrong, if anything gets wrong, automatically the final result will be deviated. Okay, so hope you understood and enjoyed the session. So let's stop here, and if you are having any doubts regarding this procedure, feel free to post your doubts in the comment section. Definitely I will try to clarify all your doubts. And if you really enjoyed my session, like my session, share my session with your friends, and don't forget to subscribe to our channel. Thanks for watching. Thank you very much. So today we'll see one more problem in dynamic programming in algorithms concept, that is longest common subsequence among 2 strings. Longest common subsequence right? So we'll see what is exactly about this longest common subsequence, and then we'll solve a problem. Okay, so the first and important point we have to know is there is a difference between a substring and a subsequence. Okay, so subsequence is different from substring. Okay, so most of the people will confuse about this substring and subsequence. For example, let us take AB, CB as string 1 and some random numbers, string 2. So let us take these 2 strings. Okay, 2 strings. So here, first, what is a subsequence and what is a substring? You can see, let us take some AB, right? So we are having in both the strings we are having the A and B, right? So AB we can call it as a substring, okay? AB we can call it as a substring, common substring in both the strings. And if you observe here, then how it differs from subsequence? So sequence means order in which we are arranging the alphabets or characters or numbers or anything, right? Elements. In general, we can call it as elements. So arranging the elements in an order, right? So sequence. So we need to find whether there is a sequence or not. Okay, first let us take A. Okay, so A, B. In this we can see the particular sequence. That means A should appear first and next B should appear. Okay, so in between there can be any number of elements, no problem. Okay, that means there should not be a consecutive, there may not be a consecutive. Okay, so in between the alphabets or in between the elements there can be anything, but only one thing we have to check: the first A should appear and then B should appear. That means before B, A should appear. So here A we are having, and then B, AB. Okay, AB is one subsequence. And what about C? A, B, C. A, B, C. And here we are having A, B, and after that we are not having C. In the second string we are having a C, and after that we are getting A and B. So we can't tell that A, B, C as a subsequence. Okay. And see, let us start with the B. Let us start with the B. So B afterwards C. You can observe here B afterwards C. Yes. So that will be a subsequence. And B, C, and again we are having a B. So here also we can observe B, C, again we are having B. Okay. B, C, again we are having B. So there is a sequence. So even though in between B, C, B we are having some more elements, right? That doesn't bother about that, right? Subsequence means you have to follow the sequence, whether the elements are following the sequence in the second string or not. So B, C, B, yes. And if you start with the C, so C followed by B, you can observe C is here and followed by B. Okay, B appears after C. Yes, correct. So CB. CB is one more sequence. Next, CB, and there are no other elements, right? Next, last one is a B. So here the last one is a B. You need not write that. So these are the common subsequences. Common subsequences. You can see. So first one A, B. So B should appear after A. So here also B is appearing after A. Here also B is appearing after A. B, C. C before B, right? C before B, right? B, C, B. B, C, B, yes. Next, C, B. If you take a randomly, take this one, A, B, C, B. So A should appear, yes, we got it. Next, B should appear, yes, we got it. Next, C. So there is no string, right? So in the second string, C is appearing before A and B. So A, B, C, B is not a subsequence, only this one. And among this one, the longest common subsequence. So this is the longest common subsequence because it is having some 3 elements. So I am generally writing it as elements. You can consider it as characters or numbers. Okay, right. So how to find all these things? How to find all these things? So just we have to remember 2 formulas, and first of all we need to draw a matrix. Matrix means rows and columns. So towards the rows we have to write down one string, towards the columns we have to write down another string, so that we'll get some matrix, 2 by 2 matrix. Okay, see, first what is the length of this string? You can consider the same string. So length is 4, and here the length of this one will be 1, 2, 3, 4, 5. Now the matrix, we have to draw the matrix with 4 by 5. So you can draw either 4 by 5 or 5 by 4. So you can go with a 4 by 5 or a 5 by 4. So if you go with a 4 by 5, so number of rows will be string 1. Number of columns will be string 2, and here also number of rows will be string 2, number of columns will be string 1. Okay, so like this we have to first draw the matrix. Okay, right. First we will draw the matrix. Right. See, I'll write here. So A, B, C and B. And here I'll write B, D, C, A and B. So first design a matrix, a table, and then we'll start the procedure. We'll see your formulas and then we'll start the procedure, how we can find out the longest common subsequence. Right. So you can observe here. So extra we have written one column and one row. You can observe here, right? So this is again separate column and separate row. Right? So initially fill all these first row and first columns with zeros. First rows and first column with zeros. And towards this one it is string 1, and towards this one it is string 2. Right? Now let us see, the index is I and here the index is J. Okay, how can we represent this particular box? So corresponding rows and corresponding columns. Okay, so this particular portion we can represent with corresponding rows and corresponding columns. So for everything we will get some I value and J value. Consider it as an index. Okay, simply you can consider it as an index. So I, J can represent the corresponding column. Now what are the two formulas we have to remember? So I'll write the formulas here. If, okay, so consider S as a string. Okay, so S of I is equal to S of J. Consider any string. So this is a string or a character, whatever it may be. So S means this one, A. Here S means this one. So S of I is equal to S of J. Then what we have to do? So we have to add with LCS. So this is usually called it as a LCS. So longest common subsequence, LCS. LCS of string of I minus 1, J minus 1. So we need to find out, or we need to add one number to this particular box. So this particular column, okay, this particular cell. So 1 plus LCS of S of I minus 1, J minus 1. Similarly, the next part, if S of I not equal to S of J, what we have to do? So we have to select a maximum value among LCS of S of I minus 1 J or S of I J minus 1. Okay, I J minus 1. For example, let us consider 0, 0, 0, 1, 0, 2, 0, 3, 0, 4. And here 1, 0, 1, 1, 1, 2, 1, 3, 1, 4. 2, 0, 2, 1, 2, 2, 2, 3, 2, 4. For example, consider. So if you want to fill this particular position, so here just remember two things. Means 0, 0 means ith row, jth column. 1, 0, first row, 0th column. Okay, and this one 2, 2, second row, second column. Okay, second row, second column. So we are starting from 0, and initial first row and first column, just avoid it. Okay, starting from this one. So 0, 1, 2. So second row. 0, 1, 2. So second column. Right? So let us assume that. And we will see this formula. 1 plus LCS of S of, for example, if you consider 11, here S of I is equal to S of j. Okay, so S of I is equal to S of j. S of 1 is equal to S of 1. What we have to do? If both are equal, we need to add 1 plus LCS of S of I minus 1. I minus 1 means S of 0, j minus 1, 0. So if you want to, if the elements are equal, S of I and j, both the elements are equal, that means these characters, okay, these characters are equal, then we have to add 1 to this particular element. So S of 0, 0, 0, 0 means this one. So diagonal, okay, we have to add to the diagonal. For example, if it is not equal, then what we have to do? So we have to go with this one. So LCS of, maximum of, if both are not equal, for example, let us take S of 2 and S of 2, consider this one. Okay, now what happens? We need to take maximum of LCS of I minus 1, 2 minus 1, 1, j, 2, or LCS of I, 2, j minus 1, 1. So we need to consider 1, 2 and 2, 1. So 1, 2 and 2, 1. So we are checking about this particular cell, and if both the elements are not equal, okay, if both the elements are not equal, so for example, consider this one, S1 is equal to S2, okay. So if both the elements are not equal, then we have to check the maximum of either previous row or previous column. So the same thing, see, 1, 2, 2, 1. So 1, 2 means this one, 2, 1 means this one. So we need to remember these two formula, and we have to fill out all the table. So just for reference, I have written the indexes. Okay, so usually we should not write the indexes. We have to fix the values. So all positions initially 0. So that's why we have added a first row and first column with zeros. Okay, now we have to traverse. So how? See, A and B. Okay, A and B. Here I'll write the strings 1 so that we can erase the portion. So string 2 is B, D, C, A and B. So I'll erase this one so that there will be no confusion, and we can simply use about, right? So string 2, see, this one is string 2 and we are representing it as J. Okay, so now we can observe A and B. Okay, we are comparing the elements A and B. So that is nothing but S of I comma is equal to S of j. So A, B, both are equal or unequal? Obviously these two are unequal. So if these two are unequal, what we have to do? So we have to add if both are not equal, then we have to do maximum of LCS of I minus 1 j, I and j minus 1. So obviously we have to select either portions. Okay, either portions. So either portions means we have to select the maximum of either this portion or this portion. So diagonal. So both are equal. Okay, both are equal. What we have to do? So we can take any of these things. So let us take this one and let us assume we have taken from this particular cell. Okay, we have taken this particular cell. So give an arrow mark through which direction, through which cell we have taken. And next, A and D. A and D. Compare A and D. Here also not equal. Then we have to apply the second formula so that these two positions will get. So among these two, which is the maximum? Both are equal. So you can select either. So I'll select from this cell itself. Again I am selecting only this one, so I am writing this arrow mark. Else, if you consider here, from here you have to write the arrow mark in this way, because we are considering this 0 from this particular cell. Okay, so anything we can do, no problem. So I will select from here, and A and C again both are not equal, so then again compare and select the either. So again I will take 0 and both are equal from this cell. Now A and A both are equal. So if both are equal, we have to add to S of I minus 1, J minus 1. So what we have to add from here, diagonally we have add. So here 0, it becomes 1, and the arrow mark should be in a diagonal position. Okay. So 1, and in this way we have taken 1. Now A and B both are not equal, so we have to compare and we have to take the maximum of diagonal. So here we are having 1, here we are having 0, so a maximum of 1 comma 0, so obviously we have to consider 1. So I will consider 1, and that is from this cell. Okay, so hope you understood. Very simple. So just applying these two formulas. Now coming to this one, B and B both are equal. So in the diagonal, so we have to add 1 to I minus 1, J minus 1. So this one. So this becomes 1, and we have taken this from diagonally. And next, B and D both are unequal. So if it is unequal, we have to consider a maximum among these two cells, I minus 1 J, I J minus 1. So these two cells. So it is 1, and I have taken from this cell. Okay, coming to B and C, both are unequal. Again, in the diagonal 0 and 1, we have to consider 1, and I have taken from this cell. And again, B and A, both are unequal. So diagonally, here we are having 1, and here we are having a 1. So both are equal, we can consider anything, right? So I will consider here 1, and I will consider from this cell itself. You can also consider, you just try at home by considering this one. Okay, no problem. Now B and B, so both are equal. Then we have to add 1 to the I minus 1 and J minus 1. So here 1 it is there, now it becomes 2, and I have taken from this particular diagonal position. Next, C, B both are not equal, so I have to consider either from 0 or 1. So diagonal, we have to consider the maximum, and 1 is the maximum. I take 1, and from this cell, so arrow mark will be towards upward. So C and D both are unequal, both are 1s, so same thing, and we can consider any value, right? Any cell. Next, C and C both are equal. Now we have to update, that means we have to increment by 1 of this particular diagonal element. So it becomes 2, and here we have considered like this. Okay, next, C and A both are unequal. So 1 and 2 are there diagonally, so we can consider the maximum. So I will consider 2, and this is from this cell. And C and B both are unequal. So here in the diagonal, both are having the same value. So you can consider anything and use an arrow mark. Now B and B both are equal. So increment the diagonal element 0. So 0 will become 1, and arrow mark will be like this. And B and D both are unequal, right? B and D both are unequal. So among these diagonal, we have to consider 1, and I am considering from this cell. And B and C both are unequal. So 1 and 2 are the diagonal elements. So 2 will be the maximum. I am considering this way. And B and A both are unequal. So both are unequal means again we have to consider the maximum among the diagonal 2 and 2. So both are equal. So I will consider the same thing. So I will consider from this one. Okay. So B and B both are equal. So increment the diagonal element. So 2, and it will be 3, and in the diagonal. So now we have filled the complete table based upon, with the help of these two formulae. Okay, if both the elements are equal, then increment the diagonal element with 1, and if both the elements are not equal, so select the maximum value among the just previous row or a previous column. So now what is the maximum value? 3, and starting from 3, follow the arrow marks. If there is a diagonal, write down the element there. If it is a diagonal, write down the element. So important, right? Point. If there is only a diagonal, then only we have to write down the element, and that element should be written from right to left. So here we are having a diagonal, right? So this 3 we got from this particular cell. Okay, this 3 we got from this particular cell. So what we have to do? We have to select the element B. Okay, now we are at 2. There is no diagonal, so we should not consider it. So from 2, the arrow mark is this one. That means we got 2 from this particular cell. So consider now this cell. Okay, this cell. So here we are having a diagonal. So we got this 2 from this particular diagonal element. So what is the value? C. So write down here C. Now we are at this position. Here the arrow mark is not diagonal. So we got this value from this particular cell. So moving towards this one. Right? So here again we are having some diagonal. That means we got this with this one. Okay, B. So write down here B. Now we are at this position, and here the weight is 0. So the longest common sequence is BCB. Just now we have seen the longest common subsequence. So just following the same way. Okay, right? So in this way we can solve the longest common subsequence. So just we have to iterate both the I value and j value. Right? So this is also a recursive function. From the previous cell we are using the value. So we are updating 2 from this particular cell. That means the result of this cell is already been saved. And from here we are updating here. And from this cell we are updating into 3. Right? So hope you understood this one. So the longest common subsequence among these two strings. Longest common subsequence is BCB. Among these two substrings. It is BCB. Okay. So you can consider any two substrings and try out this particular method, so that definitely you will get the longest common subsequence, and we can get a multiple long common subsequences also. Okay, if it is having a multiple paths, automatically we can get a multiple common subsequences. So in our next session we will see such type of strings which can lead to multiple longest common subsequences. Today we will see one more example on longest common subsequence problem using dynamic programming. So we usually call it as LCS problem. So which is the longest common subsequence, right? So first we need to take two different strings and we need to find what are the common subsequences. Okay, so in our previous session we have discussed about this one. So the difference between subsequence and the substring. So coming to the subsequence, the order of elements can be any, we have to follow the order of the elements, not the consecutive elements. Okay, so that we have seen in our previous session. I'll post the link in the description box. Please follow that, and that you can listen. So we have taken two different formulas in order to fill the 2 by 2 matrix. Okay, see, let us take the strings. Consider str1, a string as AB, C, B, D and AB. And coming to the string 2, BD, CA, BA. Okay, so these are the two different strings. Now we have to find out the longest subsequence among these two strings. First we have to draw the horizontal and the vertical lines. I'll write here A, B, C, B, D, A and B, and here I'll write so initially take it as zeros, consider initial values as zeros. Right? So in the vertical we can write it as B, D, C, A, B and A. Consider the boxes. We need to fill all these columns, and these columns should be filled with the help of two formula. So here also initially we are taking it as zeros, initial. Okay. So we have taken the complete cells, and now we need to fill all the cells by using two formula. The first one, if xi is equal to xj, if both are equal, then the cell value will be, okay, we can write it as cell of I j will be 1 plus cell of I minus 1 and j minus 1. So we need to add one element, 1 to the cost of I minus 1 and j minus 1. And the second one, if I not equal to j and both the elements are not equal, then the cell cost of ij will be a maximum of cost of I minus 1 j or c of I and j minus 1. Among these two we have to select the maximum. Okay, select this one, B and A, right? So let us consider this as x and this one as y. So xi, xj, sorry, I think is y, and here also y. Right, A and B both are compared, and we know that both are not equal. So we need to consider a maximum of I minus 1 j and j minus 1. So we have to consider I minus 1 j. So let it be I and let it be j. I minus 1 means this one. J minus j means this one. And I minus 1 j or I j minus 1. So both the cells are this one, diagonal cells. So here we are having the same number. So what we have to do? We can take any value. So I will consider this one and just place the array from which cell we are taking this. I am taking this from this array, from this cell. Now B is compared with B. Both are equal. Then we have to add 1 to the cost of I minus 1 j minus 1. I minus 1 j minus 1 means this one. Okay, this diagonal. So we need to add 1 to this particular diagonal. So 0. So now it will be 1 and we have taken it from diagonal position. Okay. Now B and C both are not equal. Among these two, which one is the max? 1. So I will take 1, and we have taken this from this particular cell. And again B and B both are equal. So we need to add this one. 1, and we got this from the diagonal. And B and D both are unequal. So we need to consider a maximum from either this cell or this cell. So 1 is a maximum, and we have taken this from this cell. And B and A both are not equal. So we have to select maximum among these two cells. I will consider this one because 1 is a maximum among 0 and 1, and we have taken from this cell. Now again B and B. So we have to add 1 to I minus 1, j minus 1. So this one is I minus 1, j minus 1. So obviously it will be 1, and we have taken from diagonal position. Now coming to the second one, DA both are not equal. So what we have to do? So we have to consider the maximum among this one and this one. So both are equal. I am taking here, and I am taking from this cell. D and B both are unequal. So from these two diagonal positions, we have to consider a maximum. 1 is a maximum. I am taking 1, and we have taken it from top cell. Okay. So put the arrow mark towards the upward. Next, D and C both are unequal. We need to consider a maximum among these two diagonals. So both are 1s. So obviously the result will be 1, and we can consider it from any cell. You can write the leftward arrow or upward arrow. Next, D and B both are unequal. Again we got 1. So I will take 1 from this particular cell. D and D equal. So we have to add 1 to C I minus 1, j minus 1, which is this one. So 1 plus 1, it becomes 2, and we got 2 from this here. So D and A both are unequal. Among these 1 and 2, we have to consider a maximum. I will consider a maximum as 2. We got this from this cell. D and B both are unequal. Again 1 and 2 are there. Diagonally we need to take maximum. I will take a maximum, and I am taking from this particular cell. Now C and A both are unequal. So if both are unequal, we have to consider a maximum among diagonal. Both are zeros. Again I will consider 0. I will consider from this cell. Or okay, you can also consider from this particular cell. No problem. C and B both are unequal. 0 and 1 diagonally we are having 2 values. Among these two we have to select the maximum. So I am considering 1, and we have considered from this particular cell. C and C both are equal. So we need to add 1 to I minus 1, j minus 1, which is this cell. So 1 plus 1, it becomes 2. We got 2 from this particular cell. And C and B both are unequal. And 1 and 2, we need to choose a maximum among this 1 and 2. So 2 is a maximum, and we got this from this particular cell. And C and D both are unequal. Among the diagonal, we have to select the maximum. So both are equal. So we can select 2 either from this side or this side. I consider this side. No problem. Anything. And C and A. So C and A both are unequal. We are having a diagonally 2 and 2. So we can consider 2, and we can select either. C and B both are unequal. 2 and 2. I consider 2, and let us consider upwards. No problem. And A and A both are equal. So we need to add 1 to C I minus 1, j minus 1, which is this cell. Here it is 0. Now it becomes 1, and we got 1 from this cell. And A and B both are unequal. So we need to select a maximum among diagonal 1 and 1. So both are equal. So we can consider any cell. So A and C both are unequal. 1 and 2 are diagonals. We need to select a maximum among these 1 and 2. So I will select 2, and this comes from upward cell. And next, A and B both are unequal. Again we are having a 2 and 2. We can select any. Both are equal. We can select any number. Okay, I mean the number from any cell. So I will consider from this one. Next, A and D both are unequal. Again diagonally we are having 2 and 2. So from this we got a 2, and I will consider from this cell. A and A both are equal. So we need to add 1 to the I minus 1, j minus 1. That is a diagonal here. So 2. So 2 becomes here 3. We got 3 from this particular cell. And next, A and B both are unequal. Among these diagonal 2 and 3, we have to consider a maximum. So I am considering 3, and that we got from left side cell. And B and A both are unequal. So 0 and 1 we have to consider maximum. I consider maximum, and we got this one from upward cell. B and B both are equal. We need to add 1 to diagonal. So here it is 1. So after adding 1 it becomes 2. So we got 2 from this particular cell. And B and C both are unequal, and diagonally we are having a 2 and 2. So both are same, we can consider it as a 2 and we can consider any cell. And B and B both are equal. So obviously this diagonal position we need to add 1. So 2 becomes 3, and here from this cell we have considered the 2. Next, B and D both are unequal. So here diagonally 2 and 3 are there. Among 2 and 3 we got only 3. So we have to consider a 3 which is selected from left cell. B and D both are unequal. B and A both are unequal. Here diagonally we are having the same number 3 and 3. So we can select any number from any cell. I consider this one. And B and B both are equal. Diagonally it was 4. So we have to write it as a 4, and we got it from diagonal. Next, A and A both are equal. Diagonally 0, it becomes 1. So from here we got it 1. Next, A and B both are unequal. So among 1 and 2 we need to take the maximum. So 2 is a maximum. I am considering 2 with this particular element. So A and C both are unequal. Diagonally we are having the same element. So we can take the same element from either cell, either left cell or up cell. And A to B both are unequal. Again we are having 2 and 3. Among 2 and 3, 3 is the maximum selected from up cell. A and D both are unequal. We are having a diagonally both are equal, 3 and 3. So obviously we can consider 3 and we can select any cell. A and A both are equal. So if both are equal, what happens? Diagonally 1 should be added to I minus 1, j minus 1. This is I minus 1, j minus 1. 1 should be added to 3. So it becomes 4, which is a diagonal position. And again A and B both are unequal. So we need to select a maximum among these two diagonals. So same value which we are taking from 4. Wait. See, here we need to select the last one. A and B both are not equal. Okay, A and B both are not equal. So we need to select either this cell or this cell, because here we are having a both 4, right? So we need to select the maximum, and here we are having the same number. So we can select the 4, and either from left cell or up cell you can select anything. So if you consider the left cell, so in such a situation you can get a more than one longest common subsequence. Okay, we are having two paths. Either we can go with the left cell or you can go with the up cell. So first case, if you are selecting this particular cell, that means the left cell, what is the longest subsequence you can see? So left cell, if you consider a left cell, okay, so what happens? So from here we need to start traveling. So this one and this 4 comes from this cell. So here we got a change. So which is A. Okay, now we are at 3. This cell comes from here 3 and again diagonal. So this cell comes from C. So here there is a change. So B, and writing everything from right to left. Okay. So we are at 2. Now we have considered it as 2. Okay. And here this cell we got from this particular cell. So there is a change. So that is C. 1. So this we have considered 1. So here this cell we had got from A. It was updated. That means a change. So we have to consider this a B. Okay, the left cell. This is the longest common subsequence among these two strings. You can see B, C, B, A. So the same order it was following from string 1 and string 2. In both the strings, the same order. So B followed by C, followed by B, followed by A. Here also B followed by C, followed by B, followed by A. So we are not considering the substring, we are considering the subsequence. So whether it is following the same sequence or not, right? Next, so if you consider it as an up cell, so if you consider it as an upward cell, if the last cell was taken from upward. So if the arrow mark is from this side, we can check. So this cell we got from this one, and here it is changed from the A. So what is this one? B. Now we are at A. So the direction, just follow the direction. And we got a 3 updated from D. So here we have to select A. Okay. Next, this one we got from this cell. So which was not updated. Again, this was appeared from this particular cell, which was updated, right? So now it is C. Now we move to 1, and this cell we got from above cell, right? Here we got. Here there is a change. It was updated from A to B, right? So we need to consider B. Now we are at A, which is 0. So this is also the longest common subsequence. How we can check? We can check. So check the same thing in the strings. First B, yes, followed by C, yes, followed by A, yes, followed by B, yes. So the order is same here also. Here also the order is same. So B followed by C, C followed by A followed by B. So both are the longest common subsequences. So this is an example where we can get multiple subsequences. Okay, it's not limited to only one subsequence. So we can get maximum subsequences with the number of elements. So if it is a longest subsequence, 4 element subsequence, we are getting a 2 answers, so 2 solutions. Okay, so hope you understood. So first we need to draw the table and initialize it with the zeros for first row and first column, and then use these 2 formulae to fill each and every cell, and use the arrow marks in order to travel from bottom to top. Here also we need to write the solution from right to left. Write down the elements from right to left. So BCBA is one solution, BCAB is another solution for these two strings. So there will be a more number of subsequences, but this is the longest common subsequence. Hello friends, welcome back to our channel. So today we'll see one more problem in algorithms concept, that is multi-stage graphs problem. Multi-stage graphs. So here the name itself indicates the multi-stage graph, means here this is a graph problem. It is a graph problem. And what is this problem? And here we need to find the shortest path from source to destination. So already we have solved the similar problem by using a different methodology, by using the greedy methods. But here we are supposed to solve this one by using the dynamic programming, right? So finding shortest path from source to destination. So here we are having a few constraints. In order to find the shortest path, we are supposed to have some constraints. So that is, we need to use the weighted and directed graph. So only we have to take the weighted and directed graph. And here the vertices will be divided into different stages. Okay, so some sort of partitions, right? So vertices were divided into partitions called stages. So each stage will be having a subset of vertices, and so the direction should be only one word, right? So if the direction is from current vertex to the next vertex, so there should not be an edge between next vertex to the current vertex. So I'll show you the example so that you can understand. So if the graph is like this, so if A, B, and let us take this C, D, okay. So these are our different vertices, okay. If there is an edges like this, okay, so this is one partition, this is another partition. So here we can say K1 is a stage, K2 is another stage, and K3 is another stage. So in this stage K1 we are having one vertex, in K2 we are having two vertices, in K3 we are having one vertex, and there should not be direction in this way. So in this example you can see the direction is towards the destination, right? A to B or A to C, and B to D or C to D, and the direction should not be like this. So one is towards destination and another one is towards the source. So this type of graph is not applicable, right? So the direction should be towards the destination only. For example, let us take this as a source, right, and this as a destination. Then the direction should be towards the only destination, not towards the source. And also every edge should have a weight. For example, the weight is 5, 2, 3 and 6. So you can call them as a weight or a cost or a distance, anything, right? Weight, cost or a distance. So there should be this one. So such type of graph we can call it as a weighted directed graph. So here we are having the directions and also weight for each and every edge. So this will be the weighted and directed graph. So in order to solve this graph problem, multi-stage graph problem, so the graph should be weighted and directed, and the partitions, the complete vertex should be in partitions called as stages, and the direction should always to be towards the destination, right? Then we can solve this by using the dynamic programming, and such type of problems can be solved by using two approaches. One is forward approach, another one is backward approach. So if you are using this forward approach, we are supposed to select the destination first and we need to solve the problem. So that we call it as a forward approach. Don't get confused. In the forward approach, we are supposed to start our process from the destination itself. And if it is a backward, we have to start from the source itself. Okay, now in this session we will see the forward approach of solving this multi-stage graph problem. So let us take an example and we will solve this multi-stage graph problem using dynamic programming using this forward approach. So come up with an example. See, let us solve this example. So this is a weighted and directed graph. You can see the directions, and also for every edge we are having some weight or cost or distance, right? And also all the directions are towards the destination. For example, consider this as a source and this one as a destination. Alright. Now we need to find the shortest path from source to destination, right? So based upon the edges. So we can start from source and we can reach the destination in different paths. We can go with A to B, B to F, F to H, or A to B, B to E, E to H. See, A to B, B to E, and E to H. A to C, C to F, F to H. A to D, D to G, G to H. Similarly, A to C, C to E, E to H. So like this, we will be having a lot of solutions, lot of possible paths, right? But we are supposed to select the path with an optimized route. That means the weight, the cost should be a minimum. That means that we call it as a shortest path. So such type of problems we can say them as a optimization problems. So where the problem is having a lot of solutions and we have to select a solution based upon the constraint. So here also the constraint is shortest distance, shortest path, right? Now let us check here how many stages we are having. Let us assume this is a stage 1 and this is stage 2, this is a stage 3 and this one is a stage 4, right? Let us assume K as a stages. So there are 4 stages. So K1 is having only 1 vertex, K2 is having a 3 vertices, K3 is having a 3 vertices and K4 is having only 1 vertex. So we need to start from the destination if we are going with the forward approach. So let us go with the K4, right? So we can call it as a cost of K4 comma what is a vertex H. We need to find out the cost for K4 to H. So where the formula will be the distance of H to H. So which we can call it as a cost. Okay, cost of H and H. So the destination and source are both are equal, then obviously the weight is 0, right? If the source and destination both are equal, then we can say the weight is 0. So it will be 0. Now, any other vertex available in K4? No. Now we can move with the K3. So K3, the cost of K3 comma, let us find out for E. Okay, then what is this one? So cost of E to destination, right? So E to destination, what is the cost of E to destination here? The distance from E comma H plus cost of H comma H. So here we are having the destination, so E to H and H to H. For example, if it is B, we need to find out the B to E plus the cost of E and H. Okay, hope you understood. So we need to find out the distance from B to H. Then obviously we can say the distance of B to E and from E to H. So similarly, if we are finding the cost E comma H, then the distance of E to H and the cost of H and H. If we are having a multiple paths, we need to find out the minimum. So what is the value here? So DE comma H 18 plus, we need not find out the value once again because already we have calculated here. So that is an advantage of dynamic programming. So we are supposed to solve the problems and save the solution in order to avoid the calculation. Once again the calculating the same problem. So here cost of H is 0, which is 18. So is there any vertex in K3? Yes, F is there. So once again cost of K3 comma F. So which means cost of F to destination is equal to the distance from F to H plus a cost of H to H. So what is the distance of F to H? 13 plus cost of H to H. It's 0, which is 13. Next, again we need to find out the cost of K3 comma, there is one more vertex G. So cost of G to H, which we can say the distance of G comma H plus cost of H to H. So what is the value of this one? D distance of G to H. G to H, it is 2 plus 0, which is equal to 2. So we have completed the K3. Now we need to move with K2. So K2 edges are DCB. Now let us find out the cost of K2 comma B. Right? Now we need to find out the cost of B to H. So we need to find out the B to H, the cost of B to H. Now you can see, now you can understand why we are writing here this one. So B to H means, so there are different possibilities. So B to E, E to H, B to F, F to H, right? B to E, E to H, B to F, F to H. So there are multiple possibilities. Here we need to find out the minimum. So minimum of distance of BE, distance of B comma E plus, now we are at E, so we need to find out the cost of E comma H. So cost of E comma H, which was already found here, see, right? Similarly, I'll write here D of C comma E, sorry, B comma F, because from B we can reach H through E or through F, okay, two paths. So we need to find out the minimum plus the cost of F comma H. That is also we have found F comma H, right? Now calculate DBE. DBE means 4 plus cost of EH, we have found out 18. So which gives it 22. And next possibility BF, B to F, it is 11 plus cost of F comma H, which is at 13. So which is 24. So we need to consider the lowest, so the minimum. Next, there is one more edge, one more vertex in K2. Now we need to find the cost of K2 comma C. That means cost of C to H. What is the cost from edge vertex C to vertex H? So that we can also have a minimum, because we are having multiple paths, C to E, C to F, C to G. 3 possible paths are there, right? So minimum of D of C to E plus cost of E to H. Similarly, D of C to F plus cost of F to H. Similarly, D of C to G plus cost of G to H. See, there are 3 outgoing edges. So we can reach H from C via E or F or G. So 3 possibilities. So we need to find out the distance of C to E and cost of E and H. Distance of D to C and F and cost of F and H. Distance of C and G and cost of G and H. So what's the value here? What's the value? D of CE. CE is 9 plus E and H. So what's the E and H? Cost of E and H already we have find out, right? So here 18. We have calculated, so 18, which is 27. And here C and F, it's a 5 plus cost of FH, already calculated, cost of FH, which is 13. Next, D of CG, it's 16 plus cost of GH, it's 2. So how much? This is 27, 9 plus 18, which is 27, 5 plus 13, which is 18, 16 plus 2, which is again 18. So we can consider 2 possibilities. One is reaching H through F or reaching H through G. Both are equal cost. Right. Leave it. Now, is there any vertex in K2 stage 2? Yes, there is a edge. There is a vertex of D. So again, find out the cost of K2 comma D, which is nothing but cost of D to H. So here, whether it is required to find the minimum value. Whether it is required to find the minimum value? No, because only one path is there from D to H. There is no outgoing edge, only one edge is there. So we can write it as D of D to G plus cost of G to H, which gives D to G, it is 2 plus cost of G to H, again it's 2. So 2 plus 2, which is a 4, which is 4, right? So is there any vertex in stage 2? B, C, D. We have calculated B, C, D, all possibilities. So there is no vertex in stage 2. Now go with the stage 1, which is a source. Then K1, the cost of K1 comma A, which is cost of A to H. A to H. How many edges are there? 3 edges are there. So we have to find out the minimum among these 3. So minimum of distance of A to B plus cost of B to H. So we need not find again B to E and E to H. Already we have calculated everything. So A to B and cost of B to H. And see again D of A to C plus cost of C to H. Again D of A to D plus cost of D to H. So among these things we have to find out the minimum. Now find out D of A comma B. What is the distance of AB? 1 plus cost of BH. Already we have calculated somewhere. BH, cost of BH. See, cost of BH, this one. So among these two we have considered minimum. So 22, we need to consider the 22, which is a 23 cost. Now D of AC. AC is 2 plus cost of CH. So here we have calculated cost of CH. So 18, we can consider anything, right? Either, because both are equal. So I am considering 18, which is 20. Next, D of AD, A to D, it is 5 plus cost of DH. What's a DH? Once again here, B to H, C to H and D to H is 4. So it is 4, which is a 9, right? So among these 3, what is the minimum? This is the minimum. This is the minimum. So we can consider 9, and this is the first stage. So that means a source. So in order to find the path from source to destination, the minimum path is a 9, right? So we have to find out the path. So 9 means A to D. Okay. So first A to D, then cost of DH. Go to the cost of DH. Where is the DH? This one. So here DH, it is G, D to G. So after D we have to visit a G, and then cost of GH. What's the GH here? GH. So from G we can go with the H. From G we can go with the H. So among all the different paths, this one is the shortest path. You can observe A to D, D to G, G to H, which is 5 plus 2, which is 9. So if you go with A to C, C to F, F and F to H, 2 plus 5, 7, 7 plus 13, 20 it will take. And if you go with A to B, B to E, E to H, 1 plus 4, 5 plus 18, 23 it will take, right? So this is the only path which is having the shortest distance. So in order to reach from source to destination, the shortest path is A to D, D to G and G to H. Right? So here what we have to do is we have to start with the destination, and from the destination try to find out the cost from each and every stage towards the destination. So here the cost of fourth stage, which is a destination to destination, the cost will be 0. So only one node is there, right? So once again, one more constraint is here in this problem the graph should contain only one source and one destination. And coming to the third stage, from the third stage we are having a 3 nodes, and from the 3 nodes we have to find out the cost from each node to the destination, so E to H. If there are multiple paths, we need to find out the minimum. We need to consider the minimum. So how we can use? We have to find out the distance from E to H and a cost from H to H. So here you can find out, here you can understand, if you are finding the distance cost of B to H, what we are doing, we are finding the distance of B to E plus the cost from E to H. So obviously we have calculated the cost of E and H, the same value we are using here. So in the dynamic programming, the complete problem will be solved into, divided into subproblems. Those are the overlapping subproblems, and each subproblem will be solved and the solution will be stored in the memory, so that in further we can make use of that particular solution in order to get the final solution, optimal solution. So the same thing happens here. For every situation we are saving the solution. So the same solution we are using in our next recursions. Right? So hope you understood this multi-stage graph problem. Okay. So let's stop here. Hope you enjoyed the session. I'll explain you in the next session with one more complex example, right? With the different stages, by increasing different stages, so that you will be understanding how we can solve it, right? So let's stop here. If you are having any doubts regarding this problem, feel free to post your doubts in the comment section. Definitely I will try to clarify all your doubts. And if you really enjoyed my session, like my session, share my session with your friends, and don't forget to subscribe to our channel. So thanks for watching. Thank you very much. Hello friends, welcome back to our channel. So today we'll see one more example in multi-stage graph problem. So in our previous session we have seen this multi-stage graph problem. So where we have to consider the weighted directed graph. So all the vertices will be arranged in stages, in terms of stages, and the problem is to find the shortest path from source to destination. So using this dynamic programming. So in our previous session we have seen one example following the forward approach, and here also we will see the same forward approach. And here we are having a different stages. So this is 1, this is 2, this is 3, this one is a 4, and this one is a 5. So total 5 stages. So in our previous session we have seen about the 4 stages. Now we will see the 5 stages. So first we have to start with the destination, right? We have to start with the destination, and we need to find the minimum path in each and every stage. So here you can see every stage is having a different number of vertices. For example, in the first stage we are having only one vertex, that is a source, and in K5, that means the 5th stage, one vertex, it is a destination. And similarly in the stage 2 we are having 2 different vertices. Stage 3, 3 vertices. Stage 4 again we are having 2 vertices, right? And you can see B, we are having 2 possible paths. C, we are having 3 possible paths. So among these we have to find out the minimum, right? So first we need to start with last vertex, that means a destination, right? So now I will go with the K is equal to 5. K is equal to 5. How many vertices are there? We are having only one vertex, that is I. Okay, we need to find out the cost of I. So cost of I comma destination I, which is nothing but distance of I and I. So which is equal to 0. So the distance from the same vertex, if the source and destination are the same vertex, obviously it will be 0. Now, any other vertex in stage 5? No, right? Now we have to find out the vertices, the cost in the stage 4. So stage 4 we are having 2 vertices. How many vertices? 2 vertices, G and H. So we need to find the cost of G to I. G to I. Okay, cost of G to I, which gives the distance of G comma I plus cost of I and I. Okay, so which is equal to distance of G and I. It is 7 plus 0, which is equal to 7. Similarly, we need to find out the cost. Any other outgoing from G? No, leave it. So cost of H and I. So which gives the distance of H comma I plus cost of I comma I. That means the next vertex to destination. Okay, here the same vertex will be the destination, so we are getting 0. So H and I, which is 3 plus 0, which is equal to 3. So any other vertex in stage 4? No, we have covered both J and H. Now go with the next stage. K is equal to 3, which is having 3 vertices, D, E, F. So D, E, F. So we need to find the distance from the cost from D to I, E to I, F to I. So first, the cost of D to I, which will be from D of distance of D comma the next vertex, that is G, plus cost of G to I. Okay, so this portion we have already calculated in our previous stage, G to I, right? So directly we can use it instead of recalculating, right? That's what the advantage of dynamic programming. So the problem will be divided into sub-problems where each and every sub-problem will be calculated or solved, and the result will be stored in the memory, and it can be retrieved whenever it requires. So the same thing happens here. So here the cost of D to C. First let us check whether there are any other edges from D to G. How many possibilities from D to G? Sorry, D to I, right? So there are 2 possibilities from D to I, right? D to I. How many possibilities? We can go with D to G, G to I, D to H and H to I. So 2 possibilities. Among these 2, we have to find out the minimum. So the same thing happens. So I am finding the minimum value here. So D of distance of D comma H plus cost of H comma I. So we need to find out the minimum value of these 2. So distance from D to G, which is 1, plus cost of Gi already calculated 7, so which will be 8. So here you can see the distance from the cost from D to I, the cost from D to I via G is 1 plus 7, it is 8. And here D to H plus cost of, so D to H is 4 plus cost of HI, already we have computed here, right? So 3, which is 7. Which one we have to consider? Obviously 7, because among these 2 we are having a minimum. So this part we are getting 8 and this part we are getting 7. So our solution is to find the shortest path from source to destination. So that's why we need to always find the minimum value, right? So next, E, we need to find the E. So cost of E to I, that means E to destination, E to destination. So how many parts are there? Let us check here. E to destination, that means I. So one possibility, E to G, G to I, E to H, H to I. So 2 possibilities, right? So let us check minimum. We need to find out the minimum. So D of E comma G plus cost of G comma I. Similarly, D of E comma H plus cost of H comma I. So we need to find out the minimum among these two. Distance of E and G, E to G, it is 6 plus cost of GI, already it was pre-computed. So GI, it is 7. So which gives a 13 as a distance. The distance of EH, E to H, it is 2 plus cost of HI, cost of HI, it is 3. So it's equal to 5. So we got the path, this path, through this path we got a distance 13, through this path we got a distance of 5. So which one we have to select it? So 5 should be selected, right, among these two. So still any other vertex in this particular stage? Yes, F. So we need to find the F also. Cost F to I. Let us check how many edges are there from F. So F to I, how many paths? You can check. F to G, G to I. Similarly F to H, H to I. 2 paths are there, you can observe. F to G, F to H. So same D of F to G plus cost of G to destination. Similarly D of F to H plus cost of H to destination. So we need to find out the minimum among these two. What is the distance of F and G? F and G, it is 6 plus cost of G and I, which is 7. Again we got 13 as a result. Okay, then D of F to H, it is 2 plus cost of HI. So here we have computed, it is 3. So which gives a 5 as a result. So among these two, here we got a 13 and here we got a 5. Again we have to select this 5, right? Yes. So any other vertex in stage 3? You can observe in the stage 3, D, E, F. Already we have computed D to destination, E to destination, F to destination. Now we need to find out the cost from stage 2 vertices. So K is equal to 2, which is having the vertices B and C. B and C, right? Now, what we have to find? We have to find from B to I, so which is a cost of B to I. So let us check the possibilities from B to I. That means how many outgoing edges. So B to I, how many outgoing edges? So B to D, and similarly B to F. 2 edges are there. And D towards I, F towards I. 2 possible paths. So here also we have to consider a minimum. So D of B to D plus cost of D to I. Similarly D of B to F plus cost of F to I. So you can see already, so B to D, what is the distance from B to D? B to D, I think it was 2. Let us assume it as 2. So B to D, let us take it as 2 plus cost of D to I. So what is the cost of D to I? Already we have computed. So here we got 8 and 7, and we need to consider the minimum. So 7 is the final value. So it is 9. D of B to F, it is 3 plus cost of F to I. Here F to I. So 13 and 15, among these two we have to select the minimum. So it is a 5. So which is 8. So we need to consider the minimum value 8. And any other vertex in the stage 2? Yes, C. Now find out the cost from C to I. Okay, C to I. So D of, so C to I. Any other possibilities you can check. So C to D and D to I. C to E and E to I, C to F and F to I. So there are 3 possibilities here. So we need to check all those things. So C to D plus cost of D to I. Similarly D of C to E plus cost of E to I. Similarly, D of C to F plus cost of F to I. So among these things, we have to consider the minimum. Let us check the distance or the cost. So D of CD, D of CD, C to D, it is 6 plus DI. What is a DI? So here 7, which is a 13. D of CE, C to E, it is a 5 plus EI, which is again 5, which gives a 10. And D of CF, C to F, it is 8 plus cost of FI, again it is 5, so which is a 13. So among these three, which one is the minimum? Obviously 10 is the minimum. So we got 13, here it is 10 and here it is 13, so 10 is the minimum. So we are considering the 10 as a value. Now any other vertex in the stage 2, we have computed the distance or the cost from B to destination and C to destination, which are the two vertices available in the stage 2. So completed. Now come with the stage 1. So stage 1. We are having only one vertex, that is A, which is a source. We need to find the cost of A to I. So which gives the distance. So here you can see A to I. What are the outgoing edges from A to B and A to C. So we can go with A to B and followed by AI, A to C and followed by I. So two possible paths are there. Let us check. So so here the distance of A to B plus cost of B to I. And similarly, D of A to C plus cost of C to I. So among these two, we have to select the minimum. So I am writing here minimum. So we need to select only the minimum value. So here also it is a minimum value. Now D of AB is 5 plus cost of BI. So here we have computed BI, right? So here 8, we got a minimum value 8, 5 plus 8, which is 13. And D of AC is 2 plus cost of CI. So among these two we got 10. So which is 12. Among these two, which one is the minimum? 12 is the minimum. So here A is a source and I is the destination. So in order to travel from source to destination, the minimum distance or the minimum cost is 12. So now we have to backtrack to find out the path. Okay, find out the path. So this is the last stage. A is a source, last stage. So we need to stop the calculation. And here we are considering that the AC plus cost of CI. So we need to consider the edge from A to C first. A to C. And then cost of CI. Go to the cost of CI. So in that we are having a 3 possible paths. Among these 3 possible paths, which one we are selecting the minimum? That is this one, C to E. So the next vertex is E. And cost of EI. So cost of EI, again go with this one, cost of EI. Here we are having a 2 possible paths. Among these two we are selecting this one because of minimum cost. E to H. So E to H. And cost of HI. Cost of HI, go to here. So it is HI, which is the destination, this one. So this gives the optimal result. That means the shortest path from source to destination. Find out the values or weights here. A to C, which is a 2. C to E, which is a 5. E to H, which is again 2. And H to I, which is again 3. Which gives the total cost of 2 plus 5, 7 plus 2, 9 plus 3, 12. This is the minimum cost to find a path from source to destination. So here A is a source, I is the destination. So this is the forward approach where we are considering from the destination itself. So first we need to consider the destination. From that we have to go with the source, towards the source, right? So we need to compute all possible paths in all different stages. So here stage 5, only one vertex, that is the destination. In stage 4 we are having a 2 vertices G and H. In stage 3 we are having a 3 vertices D, E, F. And in the stage 2 we are having 2 vertices B and C. And in the stage 1 only one vertex, which is a source. Right? So here we are computing and we are making use of the same result in our next problems. So coming to the stage 3, we are not computing about cost between G and I. So we are considering the value of G and I from the previous result. From here we are considering. So here we are not computing the cost of D and I because we have already computed this cost of D and I in the previous result. So the problem is solved, and divided into sub-problems, and again the sub-problems have been solved and the results have been saved in the memory, and we can retrieve that results whenever it is required in order to avoid the recomputing the values. So this is called the dynamic programming. So this is the multi-stage graph using dynamic programming. Right? So hope you understood this one. Let's stop here. And if you are having any doubt regarding this multi-stage graph problem, feel free to post your doubts in the comment section. Definitely I will try to clarify all your doubts. If you really enjoyed my session, like my session, share my session with your friends, and don't forget to subscribe to our channel. Thanks for watching. Thank you very much. Hello friends, welcome back to our channel. So today we will see one more approach to solve the multi-stage graph problem. So the multi-stage graph problem means finding the shortest path from source to destination. Right? So in our previous session we have seen one approach, that is a forward approach. Now we will see the backward approach in order to solve this multi-stage graph problem. Multi-stage graph, and this is a backward approach. So in our forward approach we have started from the destination and we have traveled through the source, and now quite opposite, we have to start from the source and we need to travel through the destination. Right? So here there are a lot of stages. We can see it is 1, second stage, third stage, and fourth stage. So usually we are representing a stage with a K. So K1 is the first stage where we are having only one vertex A, and K2 is a stage which is having 3 vertices B, C and D. K3 is another stage which is having 3 more vertices E, F and G. Now H is a fourth stage, only one vertex, that is a destination. Starting from 1. So in our forward approach we have started from the destination itself. Now we have to start with the source, and the formula is same. We need to find the cost of source to destination. So here K is equal to 1, which is having only one vertex. So we need to find out cost of A to A, source to destination. So here source and destination both are equal. Obviously that will be the distance between A to A, which is equal to 0, because we are at source and we are at destination. So the distance between source and destination is 0 because both are same. Right? Now there are only one vertex in stage 1 because it is a source. So completed. Now go with the second stage where we are having 3 vertices B, C and D. So we need to find out cost of source to B, cost of source to C and cost of source to D. So one thing we have to remember, how many incoming edges for B, C and D, because we are traveling from source to B. So if B is having 2 edges, that means there are 2 possible paths from source A to B. So then we have to find out the minimum among those 2. So here we are having only one incoming edge for B, C and D, you can see. So we need not go with the minimum. So only one calculation will be there. So that will be cost of A comma A plus distance of A comma B, that means edge. And here also cost of A comma A plus distance of A comma C. Here also cost of A comma A plus distance of A comma D. So here we are at source, so that's why you need not write this one directly, we can go with the edges, right? So if you are at E, then how to reach to E? So you can reach A to B, B to E. Similarly A to C, C to E. So this we are computing here, right? So this will be the cost of A to B plus distance of B to E. That means whatever the vertex is, so just before E, that is already computed. So in the same way, now we are at A, so the cost of A to A plus A to B, cost of A to A plus A to C, cost of A to A plus A to D. So we can compute here, cost of A to A is 0, which is already computed in our previous stage. So that is a dynamic programming. So complete problem will be divided into different solutions, I mean different sub-problems, and each sub-problem will be solved and the solution will be saved in the memory, so that in order to avoid the recalculation, right? So cost of A comma A is already computed, which is 0, 0 plus distance of A and B, which is 1, so finally 1. And here cost of A to A, it is 0 plus distance of A to C is 2, so totally it is 2. And here again cost of A to A is 0 plus A to D, it is 5, so it will be 5. So in order to reach from A to B, the distance is 1, A to C it is 2, A to D it is 5. Now, so any other vertices in the stage 2? No, B, C, D. So we have found already the distance from source to B, source to C, source to D. Now go with the 3, stage 3. So what are the vertex available in D3? E, F and G. Now we need to find out cost of A to E. A to E. So how many ways we can go to E, right? So how many incoming edges? So find out the incoming edges of E. So incoming edges of E are 2. One is from B, another one is from C. So we need to find out the cost of A to B, A to C, and then the distance of B to E. So, and we have to use a minimum value, so which is the cost of A to B plus distance of B to E. Similarly, cost of A to C plus distance of B to C. So we need to find out the minimum among these two, because in order to reach E, vertex E, there are two possible paths from the source. One is through B, one is through C. So cost of A comma B already we have computed in our previous stage. Cost of A to B is 1 plus D of B, distance of B and E, it's a 4. So which is totally 5. And coming to the cost of A to C, already computed in our previous stage, it is 2, distance of B and C. Sorry, this is not B and C. C and E, right? C to E, which is, this is 11, right? Okay. B, okay. So C to E it is 9, so it is 9, which is 11. So among these two, which is a minimum? This one. We need to consider this one. Okay. Now, any other edge? A to F. Cost of A to F. So in order to reach F, you can see in order to reach F, what are the incoming edges to F? Two edges. Two edges. So what are those two edges? One is from C, okay, another one is from B. So we need to reach A to C, A to B, and then only we need to go with the C to F. So we need to find out the minimum of, so cost of A to B plus distance of B to F. Similarly, cost of A to C plus distance from C to F. We need to find out the minimum cost of AB, already computed here. 1 plus distance of B and F. B and F distance is 11. So total it is 12. Then cost of A and C. Cost of A and C already computed, so which gives a 2 result, plus distance of C and F. C and F, it is 5. So it will be 7. So we need to consider 7 itself. Okay. Now cost of, there is a one more vertex G. So source to G. So how many edges, incoming edges for G? You can see 2 edges. 2 edges. One is from C, another one is from D. So we can travel from A to C and A to D. So which one we have to pass? Okay, which one we have to select? Minimum path. So here also we need to find out the minimum value among the cost of A to C plus distance from C to G. Similarly, cost of A to D plus distance of D to G. So cost of AC already computed, which is 2 plus distance of CG. C and G is 16, total 18. So cost of A and D, is 5. Distance of D and G, is 2. So which is 7. So we need to select this one. Okay. So any other vertex, we have find out the distance from A to E, A to F and A to G. So both E, F, G all are from stage 3. Okay. So this is stage 2 and this is stage 1. This is stage 1. Right? Now going to the stage 4. So which is a destination. So here we are having only one vertex, that is H. So one constraint in multi-stage graph is there should be only one source and one destination. So if any stage is having only one vertex, that will be the destination. Now we need to find out the cost of source to destination. Source to destination. So in order to go with H, what are the incoming edges? You can see one is from E, another one is from F, another one is from G. So through E, what is the cost between A to E, A to F and A to G? Because source is A itself, right? So already these we have computed in our previous one. These we have computed in our previous stage because E, F, G all are in stage 3. So here we have computed the cost from A to E, A to F and A to G. So we have to use the already computed solution. See, so this can be a minimum of so cost of A to E plus distance of E to H. Similarly, cost of A to F plus distance of F to H. Similarly, cost of A to G plus D of G to H. So find out. We have to find out the minimum. Cost of A to E. So already we have computed cost of A to E, which is 5. We got a 2 paths, 5 and 11. Among that we have to select the minimum path. I am selecting this one. So 5 will be the cost of A to E plus D of EH. EH it is 18. So which is 23. And cost of AF already computed here. AF again we got a 2 values, 2 possible paths. One is with the 12, one is with 7. So we need to find out we need to consider the lowest path. So that means 7. So 7 plus distance from F to H. So F to H, the distance is 13. So which is 20. And similarly cost of AG. So again we are having a 2 possible paths. Among that we have to select the least possible path, which is 7. So 7 plus D of GH, which is 2. So it will be 9. So among these two, 23, 29, which one is the lowest? So this one is the lowest. So we need to consider the 9, right? So this is the only one vertex in this stage 4. So that implies this is the destination. Okay. So now what is the solution for this one? What is the path? Now what is the last one? Distance of G to H. So distance of G to H, and which is added with A to G. So go to the cost A to G. So in this A to G we have considered this one, right? So A to G, that means the distance of D and G. So D and G, which is computed with A and D. Cost of A and D, go back. Cost of A and D. So which is distance from A and D. So which is distance from A and D, right? And then cost of A comma A. So source and destination. So this is the shortest path for this particular multi-stage graph. You can see A to D, which is a 5, D to G, which is a 2, G to H, again it is 2. So totally 9 is the distance to travel from A to H. That means source to destination with a shortest path. So you can cross check multiple ways. So A to B, B to E, E to H. So it will be 5 plus 18, 23. A to C, C to F, F to H. 7 plus 13 is 20. So A to C, C to E, E to H. 2 plus 9, 11 plus 18, 29. So all other possible paths will give more than 9 distance. More than 9 distance. So only this particular path, that means A followed to B, sorry D followed to G followed to H, will give the shortest path to travel from source to destination, right? So hope you understood. Here we have taken the 4 stages. So you can remember that the same diagram we have taken for the forward approach also, and we have solved it and we got the same path, okay, for the shortest distance, right? So you can cross check. So the complete subject link will be posted in the description. So you can go through the forward approach, and now you can analyze the backward approach. So already in the forward approach we have taken one more example with 5 stages. So try to solve that 5 stages by using the same problem, same procedure. So you need to get the same path which gives the shortest distance, right? And comment your suggestions and comment your answer, whether you got, or if you are having any difficulty, post your doubts in the comment section. Definitely I will try to clarify all your doubts. And let's stop here. Hope you enjoyed the session. If you really enjoyed my session, like my session, share my session with your friends, and don't forget to subscribe to our channel. Thanks for watching. Thank you very much.